Imagine you are standing on the deck of a boat in the middle of the Pacific Ocean. It is night, the kind of night where the sky and the sea blur into a single unbroken darkness, where the only way you know the water is still beneath you is by the sound of it lapping against the hull and the gentle rhythmic rocking that has been there since you left shore. There is no city glow on the horizon, no lights from passing ships, just the stars above you, more of them than you have ever seen, and below you, the ocean. The Pacific stretches in every direction for thousands of miles. You already know this, but what you might not have considered, what few people ever stop to think about, is what lies directly beneath the hull of this boat. Right now, in this moment, there is water below your feet, and below that water, more water, and below that, more still, pressing down with the accumulated weight of everything above it, growing colder and darker and heavier with every metre of depth, until the pressure becomes something almost unimaginable, something that would crush a human body the way you might crush a grape between your fingers. The ocean covers roughly 70% of Earth's surface. That number gets repeated so often it stops meaning anything, so let me try to make it real for you. If you could drain every drop of fresh water from every river, every lake, every glacier and ice cap and underground aquifer on the planet, all of it together would amount to less than 3% of the water sitting in the ocean basins right now. The ocean holds approximately 1.335 billion cubic kilometres of salt water, a number so large that writing it out in litres would take more digits than most calculators can display. This is not a feature of the Earth's geography, it is the geography. The continents are islands. The ocean is the world, and yet we know almost nothing about it. That claim sounds like exaggeration, but it isn't. As of June 2024, according to the Global Seabed 2030 project, only 26.1% of the ocean floor has been mapped using modern high-resolution technology. The rest, nearly 3/4 of the bottom of our own planet, remains less well charted than the surface of Mars. We have clearer images of distant moons than we do of the terrain 4 miles beneath the waves off our own coastlines. The reason for this is not a lack of interest or ambition. It is physics. Water is heavy. It is opaque. It absorbs light within the first few hundred meters, and it exerts pressure that increases relentlessly with depth. Sending instruments into the deep ocean is, in many ways, harder than sending them into space. In space you are fighting gravity and vacuum. In the deep ocean you are fighting a substance that wants to collapse everything you send down into a compressed, ruined version of itself. But tonight we are not thinking about the difficulty. Tonight we are sinking, slowly, comfortably, the way you might settle deeper into a warm bed at the end of a very long day. And as we descend through the water column, I want to tell you what we pass through, because the ocean is not one thing. It is layers, like a building with floors, and each floor has its own rules, its own inhabitants, its own relationship to light and warmth and life. The first layer is the one you already know, the sunlight zone, the epipelagic, stretching from the surface down to about 200 meters. This is where almost all familiar marine life exists, the dolphins and the tuna and the sea turtles and the coral reefs. Sunlight penetrates this layer in abundance, and that sunlight fuels the phytoplankton that produce roughly half of all the oxygen on Earth. Every second breath you take, you owe to organisms in this zone. It is warm, it is bright, and it feels like the ocean. Below 200 meters, everything changes. The twilight zone, the mesopelagic, extends from 200 meters down to about 1,000 meters. Light still reaches here, but barely. A dim blue glow that fades as you descend until it is little more than a memory. The creatures here are adapted for this half-darkness. Many of them produce their own light through bioluminescence, tiny chemical reactions that create cold blue or green flashes in the blackness. If you could somehow hover in the twilight zone and turn off every artificial light, you would see a galaxy beneath you, pinpricks of living light drifting through the water like stars reflected in a dark pool. A study published in 2024 by researchers led by Dr. Danielle DeLeo at Florida International University traced the evolutionary origins of bioluminescence back approximately 540 million years to a group of marine invertebrates called octocorals. That means creatures have been making their own light in the ocean for over 500 million years, and we still do not fully understand why the trait evolved in the first place. Below 1,000 meters, you enter the midnight zone, the bathypelagic. Here there is no light at all, not a trace, not a photon from the sun has reached this depth in the entire history of the ocean. The temperature drops to just above freezing, hovering between 1 and 4 degrees Celsius, and it stays there all the way to the bottom, regardless of what the surface weather might be. If you were somehow floating in the midnight zone, you would not be able to see your own hand in front of your face. The only illumination comes from the creatures themselves, their bioluminescent lures and flashes, brief sparks in an otherwise absolute darkness. Below 4,000 meters, the abyssal zone begins, the abyssopelagic. This is the realm of the deep sea floor, the vast, flat plains of sediment that stretch across the bottom of every ocean basin. The pressure here is immense, hundreds of times greater than the atmosphere at sea level. The animals that live in this zone are slow-moving, patient, adapted to a world where food arrives from above, in the form of dead organisms drifting down from the productive surface waters. Marine biologists call this slow rain of organic material marine snow, and it is the foundation of almost all life in the deep ocean. Everything down here is waiting for scraps from the world above. And then there is the final zone, the deepest layer of the ocean, the one named after the Greek god of the underworld, the Hadal zone, the Hadalpelagic. It begins at 6,000 meters and extends down past 10,000 meters in the deepest ocean trenches. This is one of the least explored habitats on Earth. The pressure is more than 1,000 times greater than what you feel standing on the surface. It is pitch black, near freezing, and it has been this way for millions of years. The creatures that live here are so specialized, so perfectly adapted to these conditions, that bringing them to the surface kills them instantly. They are organisms that have never known light, never known warmth, never known anything but the crushing, endless dark. Fewer than a dozen people in all of human history have visited the Hadal zone in person. More human beings have walked on the moon, 12 in total, than have descended to the deepest point of the ocean. That fact still surprises people when they hear it for the first time, but it shouldn't, because the moon is easier. The moon is 384,000 kilometers away, but it is surrounded by vacuum, and vacuum, while dangerous, is mechanically simple. You build a container that holds pressure in. The deep ocean demands the opposite. You build a container that keeps pressure out. And the pressure at the bottom of the ocean, at 11,000 meters of depth, is approximately 1,086 times the atmospheric pressure at sea level, roughly 8 tons, bearing down on every square inch of surface. Building something that can survive that, with a human being inside it, is one of the hardest engineering challenges our species has ever attempted. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. I make these so you have somewhere quiet to go when the world gets loud, somewhere to sink into when sleep won't come on its own. And let me know in the comments where you're listening from tonight. I'm always curious to see how far these stories travel. Now, dim the lights if you haven't already. Let the world above the surface fade. Let the glow of the screen be the last light you see before the darkness of the deep takes over, because we are going down, and we are going to be down there for a while. Tonight, I'm going to tell you about the strangest, most disturbing and most beautiful mysteries hiding in the deepest parts of our ocean. Real stories, real science, real places that exist right now on this planet. Places that most human beings will never see with their own eyes. We are going to visit the deepest point on Earth, a scar in the ocean floor so deep that if you dropped Mount Everest into it, the peak would still be submerged by more than a mile of water. We are going to listen to sounds recorded in the deep Pacific that no one could explain for years, sounds so loud they were detected by sensors 3,000 miles apart. We are going to trace the path of nuclear submarines that sailed into the Atlantic and never came home, taking their crews and their secrets to the bottom. We are going to meet creatures that shouldn't exist, animals so strange that the scientists who discovered them struggled to believe what they were seeing. And we are going to ask the question that sits at the heart of every ocean mystery, the question that keeps oceanographers awake and sends submersibles into the crushing dark year after year. What else is down there? The answer, as far as we can tell, is that we have no idea. And that is what makes the deep ocean the last true frontier on Earth. Not space, not the poles, the water beneath our feet. Let's start at the bottom, the very bottom, a place called the Challenger Deep. The story of the deepest place on Earth begins, oddly enough, with a ship that was blown off course. In 1872, the British Royal Navy converted a warship called HMS Challenger into something entirely new. They stripped out most of the guns, installed laboratories and storage compartments, and filled the ship with instruments designed to study the ocean. It was the first vessel ever outfitted specifically for oceanographic research, and on December 21st, 1872, she sailed from Portsmouth, England, on what would become a 3.5-year voyage around the world. The scientists aboard, led by Scottish naturalist Charles Wyville Thomson, intended to measure the depth and temperature of the ocean, to catalogue the creatures living in it, and to sample the sediment at the bottom. They did not know what they would find. Nobody did. The deep ocean in 1872 was as unknown as the dark side of the moon. On March 23rd, 1875, the Challenger was sailing through the western Pacific, southwest of a chain of small volcanic islands called the Marianas. The ship had been blown slightly off its planned route, and the crew decided to take a depth sounding while they waited for better winds. They lowered a weighted rope over the side. It was a simple procedure they had performed hundreds of times before. You paid out rope, you waited for it to go slack when it hit bottom, and you measured how much rope you'd used, except this time the rope kept going, and going, and going. It fell for nearly 5 miles before it finally touched something solid. The sounding registered a depth of approximately 4,475 fathoms, which translates to roughly 8,184 meters, or about 26,850 feet. The scientists aboard the Challenger had just discovered the deepest trench in the world's oceans, and they had done it entirely by accident. What they had found was the Mariana Trench, a crescent-shaped scar in the ocean floor stretching more than 2,550 kilometers in length and approximately 69 kilometers in width. It runs through the western Pacific, roughly 200 kilometers east of the Mariana Islands, near Guam. The trench was formed by the collision of two tectonic plates, the massive Pacific Plate and the smaller Mariana Plate. At their boundary, the denser Pacific Plate, carrying some of the oldest oceanic crust on Earth, as old as 170 million years, is being forced beneath the Mariana Plate in a process called subduction. The result is a gash in the Earth's surface deeper than any mountain is tall. The deepest point within the Mariana Trench is a small, slot-shaped valley at its southern end. It is called the Challenger Deep, named after the ship that first detected it. A 2021 study, the most precise measurement to date, placed its depth at 10,935 meters below sea level, plus or minus just 6 meters, at a 95% confidence level. That is 35,876 feet, roughly 6.8 miles straight down. To put that in perspective, if you could somehow lift Mount Everest from its base and lower it into the Challenger Deep, the summit of the highest mountain on Earth would still be submerged by more than a mile of water. The peak of Everest would not even come close to the surface. At the bottom of the Challenger Deep, the water column above exerts a pressure of approximately 1,086 bars. That is 15,750 pounds pressing on every square inch of surface. It is the equivalent of stacking 50 jumbo jets on top of a single human being. The temperature at the bottom hovers between 1 and 4 degrees Celsius, barely above freezing, and it has been this cold and this dark and this heavy for longer than our species has existed. The Challenger Deep was here before the first human ancestor stood upright on the African savanna. It was here before the first primate climbed a tree. It was here when the dinosaurs walked the earth, and it will be here long after we are gone. For 85 years after the Challenger's discovery, no human being attempted to visit the bottom of the trench. It was simply too deep, too hostile, too far beyond the reach of any technology that existed. But in the late 1950s, the United States Navy acquired a deep-sea submersible called the Trieste, a cigar-shaped vessel designed by the Swiss physicist Auguste Piccard and later piloted by his son Jacques. The Trieste was a bathyscaphe, a word derived from Greek roots meaning deep ship, and it was built around a simple but radical principle. A large float filled with gasoline, which is lighter than water, provided buoyancy, while iron pellets attached to the hull provided the weight needed to sink. To descend, you simply let the heavy vessel fall. To ascend, you release the iron pellets and floated back up. There were no propellers, no way to steer. You went straight down and straight back up, and you hoped that everything between those two events went according to plan. On January 23rd, 1960, Jacques Piccard and a United States Navy lieutenant named Don Walsh climbed into the Trieste's small spherical pressure cabin and began their descent into the Challenger Deep. The cabin was just large enough for 2 men, and its walls were 5 inches of forged steel designed to withstand pressures that would instantly destroy any conventional submarine. The descent took 5 hours. 5 hours of falling through blackness, watching the depth gauge climb, feeling the temperature drop, hearing the occasional groan and creak of the hull as the pressure increased. At approximately 9,000 meters, they heard a loud, sharp crack. The plexiglass window of the entrance tunnel had fractured. The 2 men looked at each other. They were already deeper than any human being had ever gone. Turning back was an option. They chose to continue. At 1:06 in the afternoon, local time, the Trieste touched bottom at a depth of 10,916 meters, the deepest point a human being had ever reached. Through the small viewport, Piccard and Walsh peered out into the darkness, illuminated by the vessel's external lights, and saw something that changed our understanding of the ocean forever. There, on the floor of the deepest, most hostile place on the planet, was a flatfish, a living creature swimming calmly across the sediment. Piccard later wrote that in that instant, the question biologists had been asking for decades was answered. Could life exist in the greatest depths of the ocean? It could. Although scientists have since debated whether what Piccard saw was actually a flatfish or a type of sea cucumber, the fundamental discovery stood. The Hadal Zone was not lifeless. Something was living down there, in the cold and the dark and the crushing weight of 7 miles of water. Piccard and Walsh spent just 20 minutes at the bottom before releasing their ballast and beginning the long ascent. They had proven it could be done, and then, remarkably, nobody did it again for more than 50 years. On March 26, 2012, the Canadian filmmaker James Cameron, the director of Titanic and The Abyss, piloted a custom-built submersible called the Deep Sea Challenger to the bottom of the Challenger Deep. He descended alone. When he reached the bottom, at 10,898 meters, he spent several hours filming and collecting samples. He described the landscape as lunar and desolate, a vast featureless plain of pale sediment stretching to the limits of his lights. He said the feeling was one of complete and utter isolation, the most lonely place he had ever been. When Cameron surfaced and climbed out of the submersible, the first person he saw was Don Walsh, who was now 80 years old. The 2 men embraced. Walsh understood. He had been there. In April 2019, an American explorer named Victor Vescovo piloted a titanium-hulled submersible called the limiting factor to a new record depth of 10,928 meters. On the bottom of the ocean, in the deepest place any human being had ever visited, Vescovo found a candy wrapper and a plastic bag. The reach of humanity had preceded him, even here, in the place farthest removed from civilization on the entire planet. Between 2019 and the end of 2022, there were 20 crewed visits to the Challenger Deep, and the list of people who have now been to the bottom includes Vescovo, Walsh's son Kelly, and American astronaut and oceanographer Catherine Sullivan, who became the first person to both walk in space and visit the deepest point on Earth. But for all these visits, the Challenger Deep remains almost entirely mysterious. We know that life exists there. Sea cucumbers, or holothurians, are probably the dominant life form, drifting across the sediment and feeding on organic material that filters down from above. Shrimp-like amphipods scavenge the seafloor, some of them remarkably abundant given the extreme conditions. In recent years, researchers have identified giant single-celled organisms called xenophyophores, creatures that can reach 10 centimeters in diameter despite being composed of just one cell. And along the walls of the trench, hydrothermal vents pump superheated water, rich in minerals and dissolved chemicals, into the surrounding ocean. Water that can reach temperatures of 371 degrees Celsius, hot enough to melt lead, yet kept liquid by the extreme pressure. Around these vents, unique ecosystems thrive, organisms that derive their energy not from sunlight, but from chemical reactions, a process called chemosynthesis that was completely unknown to science until 1977. In July 2015, NOAA, the National Oceanic and Atmospheric Administration, lowered a titanium-shelled hydrophone into the Challenger Deep. It was the first time anyone had deployed a listening device past a depth of 1 mile. The hydrophone was designed to withstand the pressure at 11,000 meters, and it was left in place for months. Its data storage capacity filled within the first 23 days. When researchers recovered the device and analysed the recordings, they expected to hear mostly silence, or perhaps the faint creaking of the Earth's crust. Instead, they heard earthquakes rumbling through the rock. They heard the roar of distant typhoons on the surface. They heard the deep resonant calls of baleen whales, singing songs that travelled thousands of kilometres through the water. And they heard the steady mechanical drone of ship propellers, the sound of human commerce and industry, audible even at the bottom of the world. The deepest place on Earth is not silent. It has never been silent. It is full of sound, full of movement, full of life that we are only beginning to understand. And the sounds it produces, along with the sounds that reach it from the world above, are part of a much larger acoustic landscape that spans the entire ocean. Because the ocean is not just a body of water, it is a conductor, a medium through which sound travels farther and faster than it does through air, a medium that carries vibrations across entire ocean basins with startling fidelity. And in 1997, somewhere in the vast emptiness of the South Pacific, that medium carried a sound that no one could explain, a sound so loud, so strange, and so unlike anything ever recorded before that it would take scientists nearly 15 years to figure out what had made it. They called it the bloop. During the Cold War, the United States Navy built one of the most sophisticated listening systems ever created. It was called SOSUS, the Sound Surveillance System, and it consisted of arrays of underwater microphones, called hydrophones, placed at strategic locations across the ocean floor. The purpose was straightforward and deadly serious. The United States needed to track Soviet submarines. A nuclear submarine moving through the deep ocean generates sound, engine noise and propeller cavitation, and the subtle hiss of water flowing over the hull. And if you placed enough microphones in enough places and connected them to enough analysts in enough rooms, you could detect and follow enemy submarines across entire ocean basins. When the Cold War ended, much of this listening infrastructure was repurposed for science. NOAA's Pacific Marine Environmental Laboratory, based in Seattle and Washington, began using a network of autonomous hydrophones deployed across the equatorial Pacific to monitor undersea volcanic activity, track earthquake patterns, study ice noise, and listen for marine mammal populations. The hydrophones were sensitive, precise, and they were recorded continuously. They were the ocean's ears, and in the summer of 1997, they heard something that nobody could explain. On a day that has never been precisely specified in the public record, the hydrophone array detected an ultra-low frequency sound of extraordinary amplitude. It rose rapidly in frequency over the course of about 1 minute, a strange ascending note unlike any known geological or biological signal. What made it immediately unusual was not just its frequency profile but its volume. The sound was detected by sensors separated by more than 4,800 kilometers, nearly 3,000 miles. To be audible across that distance, the source had to be extraordinarily loud. The researchers at PMEL gave it a name based on the way it sounded when they sped up the recording to bring it within the range of human hearing. They called it the bloop. The bloop's source was triangulated to a remote area of the South Pacific Ocean at approximately 50 degrees south latitude and 100 degrees west longitude. If you looked at that location on a map, you would find nothing. No islands, no shipping lanes, no known volcanic activity. Just open water, thousands of miles from the nearest continent, in one of the emptiest stretches of ocean on the planet. The location was, by coincidence, remarkably close to Point Nemo, the oceanic pole of inaccessibility, defined as the point in the ocean farthest from any land. Point Nemo is so remote that the nearest human beings at any given moment are often the astronauts aboard the International Space Station, orbiting 408 kilometers overhead. Christopher Fox, the NOAA acoustics researcher who analyzed the bloop, gave a series of interviews in the years following the discovery that only deepened the mystery. In 2001, speaking to CNN, he stated that the audio profile of the bloop resembled a living creature. The rapid variation in frequency, the way the sound rose and fell, matched the pattern of biological vocalizations, the kind of sounds made by whales and other marine mammals. But there was a fundamental problem. If the bloop had been produced by an animal, the animal would need to be far more powerful than any creature known to science. The blue whale, the largest animal ever to live on Earth, growing up to 30 meters in length, produces calls that can be detected across hundreds of kilometers. The bloop was detected across thousands. Whatever had made it, if it was biological, would have to be something vastly larger than a blue whale, something that had somehow escaped detection by every ship, every sonar system, every fishing fleet, and every research vessel that had ever crossed the Pacific. The internet predictably went wild, and the speculation was fueled by a coincidence that seemed almost too perfect. H.P. Lovecraft, the American horror writer, who died in 1937, had placed the fictional sunken city of Arulie, the resting place of the slumbering cosmic entity Cthulhu, at coordinates in the South Pacific that were strikingly close to the bloop's triangulated origin. The proximity was meaningless, a quirk of geography and fiction, but it captured something primal in the human imagination. The idea that something vast and unknown was sleeping in the deepest part of the ocean, and that its voice had been captured on tape, was irresistible. It spread through forums and message boards and eventually into documentaries and mainstream media. The bloop became one of the most famous unexplained sounds in history. It remained officially unexplained for 15 years. In the years following the bloop's discovery, PMEL researchers continued to deploy hydrophones closer and closer to Antarctica, monitoring underwater volcanic activity and tracking the acoustic behavior of ice. And it was there, on the vast frozen southern continent, that they finally found the answer. Between 2005 and 2010, acoustic surveys in the Bransfield Strait and Drake Passage, the turbulent waterway between South America and Antarctica, revealed that the dominant source of natural sound in the Southern Ocean was ice. Specifically, the cracking, fracturing, and breaking of glacial ice as it carved from the Antarctic ice sheet. When the researchers compared the spectral patterns of these ice sounds with the recording of the bloop, the match was unmistakable. The frequency profile, the amplitude, the duration, they were essentially identical. By 2012, NOAA officially attributed the bloop to a cryoseism, the technical term for an icequake, the sound of a massive iceberg cracking away from an Antarctic glacier and crashing into the sea. The event was tracked further by monitoring Iceberg 5-3A as it disintegrated near South Georgia Island in early 2008, producing sounds with spectrograms that overlapped almost perfectly with the original bloop recording. The sound had travelled thousands of miles through the deep water sound channel, known as the SOFAR channel, a layer of the ocean at about 1,000 meters depth, where sound waves become trapped and can propagate across entire ocean basins without losing much energy. The bloop was loud because it was carried by the most efficient acoustic conduit on Earth. The mystery was solved. The bloop was ice, not biology. But if you are like many people who followed the story, there is a part of you that finds the explanation slightly disappointing, a part that wanted the answer to be something alive, something undiscovered, something immense and ancient, moving through the deep Pacific. And that impulse, that desire for the unknown to remain unknown, says something important about our relationship with the ocean. The bloop was not the only unidentified sound detected by NOAA's hydrophone arrays. There were others, each given a name, each carrying its own smaller mystery. The upsweep was first detected in August 1991, when PMEL began recording, which means it was already happening when the microphones were switched on. It consists of long trains of narrow-band, upsweeping sounds, each lasting several seconds, repeating in a pattern that appears to be seasonal, peaking in spring and autumn. The upsweep is usually recorded near areas of undersea volcanic activity, but researchers have never been able to pinpoint its exact origin. It is still being recorded today. It has been going on for more than 30 years. On March 1st, 1999, the array detected a sound called Julia, a strange haunting noise that lasted for approximately 2 minutes and 43 seconds. It was loud enough to be heard across the entire Pacific monitoring network. NOAA attributed it to a large iceberg running aground off Antarctica, its massive hull grinding against the seabed in a slow, agonized moan that the ocean faithfully transmitted for thousands of miles. There was the slowdown, detected on May 19th, 1997, just weeks before the bloop was recorded. Its frequency gradually decreased over about 7 minutes, like a distant engine winding down, or a massive creature exhaling in the dark. Its source was near Antarctica, and it was likely another ice event, another piece of the frozen continent breaking free and settling into the sea. And there was the train, recorded on March the 5th, 1997, a sound that rises to a quasi-steady frequency and sustains it, like a locomotive approaching from a great distance and then holding at a constant speed. NOAA attributed it to a very large iceberg grounded in the Ross Sea near Cape Adare, vibrating against the ocean floor as currents pushed against it. All of these sounds have been recorded, analysed, and in most cases attributed to natural phenomena, primarily ice and volcanic activity. But attributed is not the same as proven, and there remain acoustic events in the deep ocean that do not fit neatly into any known category. The ocean is not a quiet place. It is full of sound, full of energy, full of vibrations that travel immense distances through the water column. Whales sing songs that cross entire oceans. Earthquakes rumble through the seabed. Volcanic vents hiss and roar. Ice groans and cracks and collapses. Ships churn and pulse. Submarines hum. And sometimes, in the vast spaces between all of these known sounds, the hydrophones pick up something else, something that does not match any known source, something that rises and falls and then disappears, leaving behind nothing but a spectrogram and a question. We listen to the ocean. We have been listening for decades now, with instruments of increasing sensitivity and precision, and we have learned a great deal about the sounds it makes and the creatures that make them. But we have also learned that the ocean is far larger than our ability to listen, far deeper than our ability to understand, and far more acoustically complex than we ever imagined. There are sounds down there that we will never identify, not because they are supernatural or alien, but because the ocean is simply too vast and too old and too full of processes we have not yet observed. The sounds will continue. The upsweep will rise and fall with the seasons. The ice will crack and groan as the climate warms and the glaciers retreat. New sounds will be recorded that no one has heard before, and they will be given names, and researchers will argue about their origins, and the ocean will go on making them regardless. But the ocean does not only make sounds, it also swallows things. It takes ships and planes and submarines and human beings, and it pulls them down into the dark, and sometimes it does not give them back. Sometimes the ocean keeps its secrets for decades, for centuries, for longer than anyone has been counting. And in 1968, in the middle of the Cold War, the ocean swallowed something that the most powerful navy on Earth could not find for 5 months, something that, even after it was found, refused to explain itself. This is the story of the USS Scorpion, and the year the sea swallowed 4 submarines. The year 1968 was by any measure one of the strangest and most violent years of the 20th century. Martin Luther King Jr. was assassinated in April. Robert Kennedy was assassinated in June. The Vietnam War reached its most brutal escalation with the Tet Offensive. Soviet tanks rolled into Czechoslovakia. Riots erupted in cities across the United States and Europe, and beneath the surface of the world's oceans, hidden from the headlines and the protests and the political upheaval, something else was happening. Something that would not become fully public for decades. In the span of just 6 months, 4 submarines from 4 different nations vanished beneath the waves. The Israeli submarine, IN Esther disappeared in the Mediterranean in January. The French submarine Minerve was lost in the same waters just 4 days later. The Soviet submarine K-129 sank in the North Pacific in March, and in May, the United States nuclear attack submarine USS Scorpion went down in the Atlantic. 318 submariners died, 4 nations, 4 submarines, 4 tragedies, and in at least 2 of the cases the full truth has never been made public. The loss of the USS Scorpion is the one that concerns us tonight, because it is the one that remains most deeply wrapped in mystery, the one where the official story has the most visible cracks, the one that the ocean still has not fully explained. The Scorpion was a Skipjack-class, nuclear-powered fast attack submarine, one of the most advanced underwater warships of her era. She was 252 feet long, powered by a single Westinghouse nuclear reactor, and she could travel underwater at speeds that remain classified to this day. She carried a crew of 99 men, 12 officers and 87 enlisted, and she was armed with 6 torpedo tubes capable of firing both conventional and nuclear-tipped weapons. She had been commissioned in 1960 at the Electric Boat Shipyard in Groton, Connecticut, and she had spent most of her career operating out of Norfolk, Virginia, specializing in the development of nuclear submarine warfare tactics. By early 1968, the Scorpion was in trouble. Years of continuous Cold War deployments had taken a severe toll on the boat. There were persistent oil leaks in the machinery spaces. Seawater was seeping through the propeller shaft seal. The submarine had experienced a vibration problem so severe that the entire vessel seemed to corkscrew through the water, and the cause was never fully determined. Her operating depth had been restricted to 300 feet, a fraction of her design test depth of 900 feet, because safety checks and modifications recommended after the loss of the USS Thresher in 1963 had never been fully implemented. The crew knew the boat was in bad shape. They had taken to calling her the Scrap Iron. At least one crew member, a man named Dan Rogers, refused to deploy on the Scorpion because he believed the submarine was too dangerous to take to sea. The Navy knew the Scorpion needed a major overhaul, but the Cold War did not pause for maintenance. Every American nuclear submarine was needed at sea, tracking Soviet missile submarines, gathering intelligence, maintaining the underwater balance of power that was considered essential to preventing nuclear war. And so, in February 1968, the Scorpion was deployed to the Mediterranean Sea, leaking oil and seeping seawater and vibrating through the deep, sent on one more mission, because the strategic situation demanded it. The deployment itself was eventful. According to some accounts, the Scorpion had previously conducted intelligence-gathering missions of extraordinary audacity, including a reported northern run into Russian-controlled waters where the submarine allegedly filmed a Soviet missile launch through its periscope before fleeing at high speed. The Mediterranean deployment was more routine, but as the Scorpion headed home in mid-May, she received a final assignment. She was diverted to observe a group of Soviet warships operating near the Canary Islands, an intelligence mission that required her to approach the Soviet flotilla close enough to photograph and record their activities. After completing this surveillance, the Scorpion headed west toward Norfolk. On May 16th, she stopped briefly at the American naval facility at Rota, Spain, to drop off 2 crew members, one for a family emergency and one for medical reasons. Then she continued into the open Atlantic. On May 21st, 1968, the Scorpion transmitted a routine radio message reporting her position as approximately 50 miles south of the Azores. It was a brief, standard communication. There was no indication of any problem. After that message, the Scorpion was never heard from again. She was expected to arrive at Norfolk on May the 27th. Families gathered at the dock. Wives and children waited. The submarine did not appear. Hours passed, a day passed. The Navy initially offered no explanation. Behind closed doors, the situation was far more chaotic. Radio man Second Class Ken Labes, who was stationed at Submarine Force Atlantic headquarters at the time, later described the scene. He had never seen a captain or an admiral come into the communications centre in the 2.5 years he had worked there. Suddenly, captains and admirals were running through the facility, demanding information. Normal protocols were suspended. Something was very wrong. 5 days after the Scorpion's disappearance, the Navy publicly acknowledged that the submarine was overdue and initiated a search. But what the Navy did not reveal, what would not become public for decades, was that they already had a very good idea of what had happened and roughly where. The United States Navy's SOSUS hydrophone network, the same system of underwater microphones originally designed to track Soviet submarines that would later be used by NOAA to detect the bloop, had been continuously monitoring the Atlantic. On May the 22nd, 1968, the day after the Scorpion's last transmission, the SOSUS array recorded a series of deep muffled impulses from somewhere southwest of the Azores. The sounds were consistent with a submarine hull collapsing under extreme pressure, the acoustic signature of a boat imploding as it sank past its crush depth, the structural limit beyond which the hull can no longer resist the weight of the water pressing in on it. Enter Dr. John Craven, the chief civilian scientist of the Navy's Special Projects Division, a man who had already achieved near-legendary status in the service by using an unconventional mathematical method, essentially a form of Bayesian probability analysis adapted from gambling theory, to locate a nuclear weapon that had been lost at sea off the coast of Spain after a bomber collision. Craven applied the same method to the Scorpion. Using the SOSUS acoustic data, he and his team triangulated the likely location of the implosion sounds and calculated a probability map of where the wreckage might be found. In late October 1968, 5 months after the Scorpion's disappearance, the Navy's oceanographic research vessel Mizar, towing a deep-sea camera sled across the seafloor at over 3,000 meters depth, located the wreckage. It was almost exactly where Craven had predicted it would be. The images that came back were devastating. The hull was broken in multiple places. The sail, the raised structure on top of the submarine that houses the periscope and communications masts, had been torn completely free. The forward section had imploded, crushed inward by the pressure as the vessel sank past its structural limits. Debris was scattered across the ocean floor. There was no possibility of survivors. The 99 men of the Scorpion were gone. But finding the wreckage did not solve the mystery. If anything, it deepened it, because the cause of the sinking was not apparent from the debris field, and the Navy's official investigation produced conclusions that many people, including some of the investigators themselves, found unsatisfying. The leading theory, championed by Dr. Craven and later supported by evidence from a retired weapons engineer named Charles Thorne, pointed to the Scorpion's own torpedoes. The submarine carried Mark 37 anti-submarine torpedoes, sophisticated weapons powered by silver zinc batteries. These batteries were separated from the torpedo's power cell by an extremely thin metal foil diaphragm. Under normal conditions, the foil held the battery's volatile chemicals apart. But vibrations, the kind of vibrations that a submarine generates during normal operations, could gradually weaken the foil, causing the chemicals to interact prematurely. If the interaction was slow, it generated heat. If it was fast, it could cause an explosion. The Scorpion was known for her vibration problems. Weeks after the submarine was lost, Thorne's team at the Naval Torpedo Station in Keyport, Washington, accidentally started a fire by subjecting a Mark 37 battery to vibrations during routine testing. It was exactly the kind of event that Craven had theorized, a slow chemical interaction inside a torpedo, generating heat that eventually ignited the warhead, blowing open the torpedo room and allowing the sea to rush in. The submarine, already weakened by years of deferred maintenance, would have flooded rapidly and sunk. There is another theory, darker and more politically sensitive, that has persisted for decades. Some researchers and former Navy personnel believe the Scorpion was attacked and sunk by a Soviet submarine, possibly in retaliation for the loss of the Soviet submarine, K-129, which had sunk under mysterious circumstances in the North Pacific 2 months earlier. The circumstantial evidence is suggestive. The Scorpion had just been surveilling a Soviet naval flotilla. She was operating in waters where Soviet submarines were known to be active. The Cold War in 1968 was at one of its most dangerous points, with both navies pushing the boundaries of confrontation beneath the waves. Two former communications specialists stationed at Submarine Force Atlantic Headquarters, Mike Hannon and Ken Larbies, broke their silence years later and stated on the record that senior officers arrived at the communications center on May 22nd, already knowing that the Scorpion was lost, and that they overheard officers openly discussing the belief that a Soviet submarine had sunk her. The Navy's official court of inquiry concluded carefully and precisely that the evidence does not establish that the loss of Scorpion and part deaths of those embarked were caused by the intent, fault, negligence, or inefficiency of any person or persons in the naval service or connected therewith. It did not establish a definitive cause for the sinking. Rear Admiral Charles D. Nace, a senior member of the Court of Inquiry, later called the loss of the Scorpion one of the greatest sea mysteries of our age. The wreckage of the Scorpion still lies on the Atlantic sea floor, more than 3,000 meters down. The nuclear reactor and the 2 nuclear-tipped torpedoes she was carrying remain on the bottom. Periodic monitoring has detected no radioactive leakage, but the materials are still there, resting in the dark. The 99 men who sailed the Scorpion on her final voyage left behind 64 widows, some of them pregnant at the time, and 99 children. Most of the crew were younger than 25 years old. The ocean took the Scorpion in May of 1968, and in the more than 50 years since, it has never fully explained what happened. The theories remain theories. The evidence remains ambiguous. The acoustic recordings from the SOSUS array, which captured the submarine's final moments, have been analysed and reanalysed by generations of acoustic experts, and they can tell us approximately when and where the Scorpion was lost, but they cannot tell us why. The ocean heard the submarine die. It recorded the sound, and then it closed over the wreckage and kept it in the dark, along with all the answers for what may be forever. The Scorpion is not alone on the seafloor. The ocean floor is littered with the remains of vessels that went down and never came back. Warships and merchant ships and fishing boats and aircraft, and things that have no name. Some of them are documented, some of them have been found, and some of them are still lost, resting in depth that no one has explored. Their stories known only to the water that surrounds them and the creatures that have made homes in their rusting hulls. But the ocean does not only hold the things we have lost, it holds things we have never found in the first place. Creatures that live in the deep, in the cold, in the dark. Creatures so large and so elusive that for centuries they were dismissed as myth. Until, one by one, the myths began to surface. For most of recorded history, sailors have told stories about monsters in the deep. Enormous serpents that could wrap themselves around a ship and drag it beneath the waves. Kraken with arms long enough to reach the top of a mast. Leviathans that swallowed boats whole and carried their crews down into the darkness where no light ever reached. These stories were universal. You find them in Norse mythology and Greek legend, in the accounts of medieval travellers and the logbooks of Age of Exploration captains, in the folk traditions of every culture that has ever put a boat on the ocean. And for centuries scientists dismissed them. The sea serpents were exaggerations, the krakens were fever dreams, the leviathans were whales, seen at a distance, misidentified by frightened men on heaving decks. The scientists were right to be sceptical, but they were also, in at least one important case, wrong, because the kraken was real. It just took until 2004 for anyone to prove it. The giant squid, Architeuthis dux, has been known to science since the 1850s, when fragments of enormous tentacles and beaks washed up on beaches or were found in the stomachs of sperm whales. Entire specimens occasionally surfaced, dead or dying, found floating at the surface or entangled in fishing nets. Scientists could see that the animal was enormous, potentially reaching lengths of 13 to 20 metres, or roughly 43 to 66 feet, from the tip of its body to the end of its two longest feeding tentacles. They could see that it had the largest eyes of any known animal, eyes the size of dinner plates, evolved to capture every stray photon in the light-starved depths where it lived. They could see that it was a predator, with a sharp, parrot-like beak at the centre of its ring of arms, capable of slicing through flesh and the thick rubbery skin of other deep-sea animals. But for over 150 years, despite knowing that the giant squid existed, no one had ever seen one alive in the wild. Every specimen was dead or dying. Every photograph showed a limp pale carcass draped across a dock or spread out on a laboratory floor. The giant squid was the most famous animal on Earth that no living human being had ever observed in its natural habitat. Think about that for a moment. An animal 60 feet long living in every ocean on the planet, and nobody had ever seen one swimming. In 2004, a team of Japanese researchers led by Tsunemi Kubodera finally captured the first photographs of a living giant squid in the wild. They lowered a baited camera line to a depth of about 900 meters in the North Pacific off the coast of Japan and waited. What they captured was extraordinary. A giant squid estimated to be about 8 meters long approached the bait, attacked it, and became partially snagged on the line. The photographs showed an animal that was nothing like the pale, flaccid corpses from museum displays. It was vibrant, active, aggressive, its skin flashing with chromatophore patterns, its arms grasping and pulling at the bait with obvious muscular force. The squid eventually tore free, leaving behind a piece of tentacle that was later measured at over 5 meters in length. It was not until 2012 that the first underwater video of a living giant squid was captured, again by Kubodera's team, in collaboration with researchers from the Discovery Channel and NHK. They filmed the giant squid at a depth of about 630 meters, swimming with a slow, undulating grace that seemed almost hypnotic. The animal they filmed was relatively small, about 3 meters in body length, but it was unmistakably alive, unmistakably a giant squid, and unmistakably magnificent. We still know almost nothing about how these animals live. We do not know how they hunt in the wild, how deep they typically dive, how long they live, how they reproduce, how they communicate, or how many of them exist. An animal that can grow to 66 feet, that lives in every ocean, that has the largest eyes in the animal kingdom, and we cannot answer the most basic questions about its biology. The ocean is very good at keeping secrets, and the giant squid is not even the largest of its kind. In the Southern Ocean, in the frigid waters surrounding Antarctica, lives a related species called the colossal squid, Mesonica teuthis hamiltoni. The colossal squid can grow to about 45 feet in length, and is believed to be heavier than the giant squid, with a thicker body and shorter but more powerful arms lined with swiveling hooks in addition to suckers. It lives deeper than the giant squid, hunts in the near-total darkness of the Southern Ocean's abyssal waters, and is even less well understood than its more famous relative. Scientists have known about the colossal squid for about a century. It was first described in 1925 based on 2 tentacles found in the stomach of a sperm whale. Since then, a handful of specimens have been recovered from deep-water fishing operations, most of them damaged, most of them juvenile. But no one had ever seen a living colossal squid in its natural environment. Not once. Not in 100 years. That changed in the 2025, when scientists from the Schmidt Ocean Institute, operating a remotely operated vehicle approximately 2,000 feet below the surface of the remote South Atlantic Ocean, captured the first ever footage of a living colossal squid in the wild. The animal in the video was a baby, approximately 1 foot long, translucent and delicate looking, drifting through the dark water with an eerie, almost ghostly calm. It was a tiny thing, an infant of a species that can grow to the size of a school bus, filmed for the first time in the history of human observation. 100 years of searching, and this was what we finally found. A baby, floating in the dark, thousands of miles from the nearest human settlement. The deep ocean is full of animals we have barely begun to catalogue. In January and February of 2024, a scientific expedition off the coast of Chile, exploring the depths of the Southeast Pacific, discovered more than 100 previously unknown marine species in a single survey. 100 species that no human being had ever described or named, found in a single expedition to a single stretch of deep ocean. In November 2025, the Ocean Species Discoveries Initiative published a collection describing 14 new species from depths exceeding 6,000 meters, discovered through a collaboration of more than 20 researchers from multiple countries. Among them were a record-setting mollusk, a carnivorous bivalve, a clam that hunted, and a parasitic isopod that researchers compared in appearance to a piece of popcorn. These were not minor variations on known species. They were genuinely new, genuinely strange, genuinely unlike anything that had been documented before. And then there are the animals that defy our understanding of time itself. The Greenland shark, Somniosus microcephalus, is a large, slow-moving predator that lives in the cold waters of the North Atlantic and Arctic Oceans. It can grow to about 5 meters in length. It swims at roughly 1 mile per hour, and it is, as far as we can determine, the longest-lived vertebrate on Earth. The Greenland shark does not reach sexual maturity until it is approximately 150 years old. Its total lifespan is estimated to exceed 500 years. That estimate comes from a remarkable piece of detective work. In 2016, a team led by marine biologist Julius Nielsen at the University of Copenhagen used radiocarbon dating to analyze proteins in the lenses of Greenland sharks' eyes. The lens of the eye is one of the few tissues in a vertebrate body that does not turn over its cells. The proteins that form the lens during embryonic development remain there for the animal's entire life, making them a kind of biological clock. By measuring the ratio of radioactive carbon isotopes in these proteins and calibrating them against the atmospheric carbon spike caused by nuclear weapons testing in the 1950s, Nielsen's team was able to estimate the ages of 28 Greenland sharks caught as bycatch in fishing operations. The oldest was estimated to be approximately 392 years old, with a margin of error that pushed the upper estimate past 500. Consider what this means. A Greenland shark alive today, swimming slowly through the cold, dark waters of the North Atlantic, could have been born before the Pilgrims landed at Plymouth Rock, before Galileo pointed his telescope at Jupiter, before Shakespeare wrote Hamlet. This animal has been alive for the entirety of what we consider modern history, and it has spent every moment of that time in the ocean, in the cold, in the dark, moving at 1 mile per hour, unbothered by the rise and fall of empires and the noise of civilizations that it cannot see, and does not know exist. The ocean contains animals older than our countries, larger than our buildings, stranger than our mythology, and more numerous than our ability to count them. Every time we send a camera into the deep, we find something new. Every time we drag a net through waters we haven't sampled before, we pull up organisms that no textbook has described. The estimate is that roughly 2 million marine species exist on Earth, and only a fraction of those have been formally identified and catalogued. The rest are down there, unnamed, undocumented, living and dying and reproducing in the dark in waters that no human eye has ever seen. The deep ocean is not just a place we haven't explored. It is a place that is actively hiding from us, not through any intention, but through the sheer, crushing difficulty of access. The pressure, the darkness, the cold, the distance, these are not obstacles we can solve with more funding or better equipment alone. They are fundamental physical barriers that make the deep ocean as alien and inaccessible as any world in the solar system, and yet it is right here, beneath our feet, on the same planet where we live and work and sleep. The creatures are there. They have always been there, and most of them we will never see. But the ocean holds more than living things. Beneath its surface, scattered across the seafloor and carved into the bedrock of the continental shelves, there are structures and formations that challenge our understanding of history, geology, and in some cases, the boundary between what is natural and what might not be. In the mid-1980s, a Japanese dive instructor named Kihachiro Aratake was exploring the waters off the southern coast of Yonaguni Island, the westernmost inhabited island in Japan, located closer to Taiwan than to the Japanese mainland. The waters around Yonaguni are known for strong currents and hammerhead shark migrations, and Aratake was likely scouting dive sites when he encountered something that would spark a debate lasting more than 40 years. Resting on the sea floor at a depth of about 25 meters, he found a massive stone formation. It was roughly 50 meters long and 20 meters wide, and its surface was covered in what appeared to be terraces, steps, flat platforms and right angles, features that looked, at first glance and second glance, and even after years of investigation, astonishingly like the work of human hands. The Yonaguni Monument, as it came to be known, became one of the most contentious underwater sites in the world. To some observers, particularly the marine geologist Masaki Kimura of the University of the Ryukyus, the structure showed clear evidence of human modification, perhaps even human construction. Kimura identified what he interpreted as a road, a wall, a gate, carved steps, and drainage channels. He dated the structure to roughly 10,000 years ago, which would place its construction at the end of the last ice age, when sea levels were significantly lower and the site would have been above water. If Kimura was right, the Yonaguni Monument would be evidence of an advanced civilization older than any known in East Asia, a discovery that would fundamentally rewrite the early history of the region. Other geologists were far less convinced. Robert Schoch of Boston University, who visited the site multiple times, argued that the features Kimura identified as human-made could all be explained by natural geological processes. Yonaguni's bedrock is a type of sandstone that fractures along natural plains, producing flat surfaces, sharp edges, and angular steps as it erodes. Similar formations exist on land in other parts of the world, places where geology alone has produced features that look strikingly architectural. Schuch did not rule out the possibility that humans might have modified a naturally occurring formation, but he saw no evidence that the structure was built from scratch. The debate has never been resolved. The Yonaguni monument sits on the seafloor of the East China Sea, visited regularly by divers who swim along its terraces and photograph its sharp, geometrical contours, and it refuses to declare itself one way or the other. It might be a lost temple, it might be a trick of geology, it might be something in between, a natural formation that humans found and shaped, the way our ancestors shaped caves and cliff faces long before they built freestanding structures. The ocean, as always, is not offering answers. It is simply presenting the evidence and letting us argue. Halfway around the world in the cold, dark waters of the northern Baltic Sea, another anomalous object lies on the seafloor, and its origins are even more uncertain. In June 2011, a Swedish ocean exploration team called Ocean X, led by Peter Lindberg and Dennis Oberg, was conducting a sonar survey of the Baltic seafloor. They were treasure hunters by trade, searching for shipwrecks and cargo that might have commercial value. What they found instead was a sonar return unlike anything they had encountered before. The image showed an oval-shaped object resting on the seabed at a depth of about 85 meters. It was approximately 60 meters in diameter, roughly 200 feet, and it appeared to have a stone-like or metallic surface, with features that were not typical of natural underwater formations. Trailing behind the object was what appeared to be a track or drag mark extending for several hundred meters across the seafloor, as though the object had slid or been pushed into its current position. The Baltic Sea anomaly, as it was immediately dubbed by the media and the internet, generated a frenzy of speculation. The drag mark was compared to a crash trajectory. The oval shape was compared to the Millennium Falcon from Star Wars. Theories range from a sunken World War II era concrete structure to a glacial deposit to, inevitably, a crashed UFO. Ocean X returned to the site with divers and recovered samples, but the results were inconclusive. Some samples appeared to be natural rock, others seemed to contain unusual metallic inclusions. The team reported that electronic equipment malfunctioned near the object, although this claim has not been independently verified and could easily be attributed to the general unreliability of electronic instruments in cold salt water. As of today, no definitive scientific analysis has established what the Baltic Sea anomaly actually is. It might be a glacial deposit, a chunk of rock dropped on the seafloor by a retreating ice sheet at the end of the last ice age. It might be a natural geological formation shaped by currents and sediment. It might be a piece of military infrastructure from either of the two world wars, both of which left enormous quantities of debris on the Baltic seafloor. What it almost certainly is not is an alien spacecraft, but the mere fact that it exists, that it is sitting on the seafloor of a relatively shallow and well-travelled sea, and that we cannot definitively identify it, says something important about how little we know about the bottom of our own oceans. This object is in 85 meters of water. Recreational divers can reach it, and we still do not know what it is. The ocean has a talent for making things disappear. Not just objects, but entire islands. Tionai was an island in the Solomon Islands chain in the southwestern Pacific. According to the oral histories of the local population, it was a substantial place, large enough to support a community, and then, sometime in the past few centuries, it vanished. The island was destroyed by what appears to have been a catastrophic combination of underwater volcanic activity and a subsequent landslide that caused part of the island to slip beneath the waves. Massive tsunami waves completed the destruction. Tionai sank, and the people who had lived there were forced to relocate to neighbouring islands, carrying with them only the memory of a home that the ocean had reclaimed. Sandy Island was a different kind of disappearance. In 1774, the great British navigator Captain James Cook charted an island in the waters between Australia and New Caledonia in the Coral Sea. It appeared on his maps as a small but definite landmass, and it was subsequently reported by the crew of the ship Velocity in 1876, confirming its existence. Sandy Island was dutifully added to maritime charts and remained there for over 2 centuries. It appeared on maps published by major cartographic agencies. It appeared on Google Maps. You could zoom in on it and see a dark shape against the blue of the Pacific, labelled with its name. In 2012, a team of Australian scientists aboard the research vessel Southern Surveyor sailed to the coordinates where Sandy Island was supposed to be. They found nothing, no island, no reef, not even shallow water. The depth sounder registered more than 1,300 metres of open ocean beneath the hull. Sandy Island did not exist. It had never existed, or it had existed and been destroyed by some geological process so complete that it left no trace. The most likely explanation is that Cook's original observation was an error, perhaps a cloud bank or a volcanic pumice raft mistaken for land, and that subsequent reports simply confirm what the maps already showed without actually checking. Sandy Island was a ghost, a cartographic error that survived for 238 years, copied from map to map, atlas to atlas, database to database, until someone finally went to look and found only the sea. Bermeja was a similar mystery. This small island was first recorded in a Spanish list of islands published in Madrid in 1539, and it appeared on numerous maps from the 16th through the 20th century. Located in the Gulf of Mexico off the coast of the Yucatan Peninsula, when Mexican researchers attempted to locate Bermeja in the early 2000s, they could not find it. Repeated surveys found no trace of the island. Some geologists have suggested that rising sea levels may have submerged it. Others have proposed that it was simply a cartographic invention, an error that propagated through centuries of map-making. And there is a more colourful theory, entirely unproven, that the island was deliberately destroyed by the CYA to expand the United States Economic Exclusion Zone in the Gulf of Mexico. There is no evidence for this, but the mere existence of the theory tells you something about how the ocean's mysteries interact with human paranoia and imagination. Beneath all of these surface mysteries, at the very bottom of the ocean, there exist formations so strange that they seem to belong to another planet entirely. On the deep sea floor, in various locations around the world, there are brine pools. These are large bodies of water that sit on the ocean floor, distinct from the ocean around them, separated by a visible boundary that looks almost like an underwater shoreline. The water in these pools is so salty, up to 10 times saltier than the surrounding ocean, that it has a different density and does not mix easily with the water above it. The result is a clearly defined lake at the bottom of the sea, with its own surface and its own chemistry, existing beneath thousands of meters of ocean. Brine pools are toxic to most marine life. Animals that wander into the hypersaline water are often killed by the chemical shock. Dead fish and crabs can sometimes be seen littering the edges of the pools preserved by the extreme salt concentration, the way a pickle is preserved in brine. And yet, at the very margins of these pools, where the brine meets the normal seawater, unique microbial communities thrive, organisms that have adapted to conditions so extreme that they are studied by astrobiologists as analogues for environments that might exist on other worlds. The origin of brine pools is not entirely understood. They are thought to form when ancient salt deposits on the seafloor dissolve and concentrate, or when tectonic activity exposes subsurface salt layers to the ocean. But the specific mechanisms that create and maintain individual pools are not always clear, and the ecosystems that exist at their margins are only beginning to be explored. The ocean floor is, in the most literal sense, another world. It has its own geography, its own chemistry, its own physical laws of pressure and temperature, its own ecosystems that operate independently of sunlight and the surface world. It has lakes within the sea. It has formations that might be buildings. It has mountains that no one has climbed, and canyons that no one has mapped, and plains that stretch for thousands of miles without any human being ever having laid eyes on them. And in certain places, the ocean floor does something that overturns one of the most fundamental assumptions of biology. It creates life without sunlight, not in spite of the darkness, but because of it. Because in the crushing depths, where the Earth's crust is thin, and the mantle's heat leaks through, there are cracks in the world that pour out chemistry and energy, and life, as it always does, finds a way. For most of the history of biology, there was one rule that nobody questioned. All life on Earth depended on the sun. Plants captured sunlight through photosynthesis, converting carbon dioxide and water into sugars and oxygen. Herbivores ate the plants, carnivores ate the herbivores. Decomposers broke down the dead and recycled the nutrients back into the soil, where plants could use them again. Every food chain, every ecosystem, every living organism on the planet was ultimately powered by the nuclear fusion reactions occurring 93 million miles away at the centre of the solar system. This was not a theory. It was a fact so fundamental that questioning it would have been like questioning gravity. In 1977, that fact was overturned. In February of that year, a team of marine geologists was using the deep-sea submersible Alvin to explore the Galapagos Rift, a volcanic spreading centre on the floor of the eastern Pacific Ocean, about 250 miles northeast of the Galapagos Islands. The scientists aboard were not looking for life. They were studying the geology of the seafloor, investigating the volcanic processes that create new oceanic crust as tectonic plates pull apart. But when Alvin descended to a depth of about 2,500 meters and approached the rift zone, the researchers saw something that made no sense. Around cracks and fissures in the volcanic rock, where superheated mineral-laden water was pouring out of the Earth's crust, there were animals. Not a few scattered organisms, but dense thriving communities of life, clustered around the vents in concentrations that rivaled the most productive ecosystems on the surface. Giant tube worms, some of them over 2 meters long, swayed in the current, their white tubes topped with vivid red plumes that extracted dissolved chemicals from the water. Clusters of mussels and clams carpeted the surrounding rock, their shells encrusted with microbial mats. Crabs and shrimp scuttled across the volcanic substrate, feeding on bacteria and organic particles. Pale ghostly fish drifted through the clouds of mineral-rich fluid. None of this should have been possible. At 2,500 meters, there was no sunlight. There had not been sunlight at this depth for as long as the ocean had existed. The water temperature in the surrounding ocean was barely above freezing, and the fluid erupting from the vents was superheated, reaching temperatures that could exceed 400 degrees Celsius in some locations. Water kept liquid only by the enormous pressure of the overlying ocean. This was not an environment where life should exist. It was an environment where life should be impossible. The answer, when it came, rewrote the rules of biology. The organisms at the hydrothermal vents were not dependent on sunlight. They were dependent on chemistry. Bacteria living in and around the vents were using a process called chemosynthesis, in which chemical energy from dissolved hydrogen sulfide and other inorganic compounds was converted into organic molecules. These chemosynthetic bacteria formed the base of an entirely independent food chain, one that had no connection to the sun whatsoever. The tube worms had no mouths and no digestive systems. They did not eat. Instead, they harboured billions of chemosynthetic bacteria inside their bodies, in a specialised organ called the trophosome, and the bacteria provided them with all the nutrition they needed in exchange for a steady supply of hydrogen sulfide from the vent fluid. The worms were, in effect, solar panels turned inside out, converting chemical energy rather than light energy into life. The discovery of hydrothermal vent ecosystems was one of the most significant biological findings of the 20th century. and its implications extended far beyond the ocean floor. If life could exist without sunlight, sustained entirely by the chemical energy of the Earth itself, then the definition of a habitable environment was vastly broader than anyone had assumed. Suddenly, any world with liquid water and geological activity became a candidate for life, and in our own solar system there were candidates. Europa, the ice-covered moon of Jupiter, is believed to harbour a global ocean of liquid water beneath its frozen surface. The ocean is kept liquid by tidal heating. The gravitational flexing of Europa's interior caused by its orbit around Jupiter and the gravitational pull of nearby moons. If there are hydrothermal vents on Europa's seafloor, and the tidal heating strongly suggests there could be, then the same chemosynthetic processes that sustain life at vents on Earth could potentially sustain life on Europa. The same logic applies to Enceladus, a small moon of Saturn that was found in the 2005 to be venting plumes of water, vapour and ice particles from cracks in its southern polar region. Analysis of these plumes by the Cassini spacecraft detected molecular hydrogen, a key indicator of hydrothermal activity. The chemistry was remarkably similar to what you would find at a hydrothermal vent on Earth. Some researchers have pushed the implications even further. Patricia Fryer and colleagues at the University of Hawaii have speculated that serpentine mud volcanoes, which form near ocean trenches where one tectonic plate slides beneath another, might have provided the conditions for the very first life on Earth. The chemical reactions that occur in serpentinization, where water reacts with iron-rich minerals in the Earth's mantle, produce hydrogen and methane and create highly alkaline, energy-rich environments. These are the kinds of environments where the simplest biochemical reactions could have begun, where the first self-replicating molecules might have assembled themselves from inorganic precursors, where life itself might have started, not in a warm, sunlit pond as Darwin imagined, but in the dark, at the bottom of the ocean, in a crack in the Earth's crust. The hydrothermal vents we know about are, by most estimates, just a fraction of those that exist. The mid-ocean ridge system, the chain of volcanic mountains that runs through the centre of every ocean basin, like the seam of a baseball, stretches for approximately 65,000 kilometres around the globe, and vents have been found along nearly every section that has been explored. But exploration of the mid-ocean ridges is far from complete. New vent fields are discovered regularly. In 2016, NOAA's exploration of the Mariana Trench discovered previously unknown hydrothermal vent fields at Chamorro Seamount, west of the trench itself, with unique chemistry and biological communities that had never been documented. Each new vent field is a new ecosystem, potentially hosting species found nowhere else on Earth, organisms adapted to the specific temperature and chemistry of that particular vent. Organisms that may exist for only as long as the vent is active, which could be decades or centuries, before the geological processes that created it shift and the hot water stops flowing. When a vent dies, the community that depended on it dies too. The tube worms, the clams, the specialized bacteria, all of them perish when the chemistry that sustained them ceases. And then, sometimes, a new vent opens nearby, and the cycle begins again, colonized by larvae that have been drifting through the deep ocean, searching for the chemical signatures that tell them a new home has been born. In the waters above and around the vents, another phenomenon illuminates the deep ocean in a very different way. Bioluminescence, the production of light by living organisms, is perhaps the most widespread and least understood biological phenomenon in the ocean. In the deep sea below the reach of sunlight, the majority of organisms produce their own light. Estimates vary, but some researchers believe that 80 to 90% of all deep-sea creatures are bioluminescent. The ocean's darkness is not truly dark. It flickers and pulses and flashes with the light of billions of living organisms, a galaxy of cold blue and green fire distributed through the water column from the twilight zone all the way down to the Hadal depths. The chemistry of bioluminescence is well understood. It involves a light-producing molecule called luciferin and an enzyme called luciferase. When luciferin is oxidized in the presence of luciferase, it produces light with almost no heat, an extraordinarily efficient process. The light is typically blue or green because those wavelengths travel farthest in seawater, which absorbs red light rapidly. But the evolutionary question, why bioluminescence evolved in the first place, has been surprisingly difficult to answer. The 2024 study led by Dr. Danielle DeLeo at Florida International University traced the origins of bioluminescence back approximately 540 million years to a group of marine invertebrates called octocorals. This places the evolution of biological light production right around the time of the Cambrian explosion, the period when complex animal life first appeared in the fossil record. The connection is tantalizing. The Cambrian explosion coincided with a significant rise in atmospheric and oceanic oxygen levels, and John Copley, a deep-sea biologist at the University of Southampton, has suggested that this change in ocean chemistry may have been the trigger. Organisms in the newly oxygenated oceans may have evolved bioluminescence as a response to new chemical conditions, perhaps as a defense mechanism, perhaps as a signaling system, perhaps for reasons we have not yet imagined. The uses of bioluminescence in the modern ocean are as varied as the creatures that produce it. Some organisms use light to attract prey, like the anglerfish with its glowing lure dangling in front of its enormous jaws. Some use it to communicate, flashing patterns that signal to potential mates or warn rivals. Some use it as camouflage, a strategy called counter-illumination, in which organisms on the underside of their bodies produce light that matches the dim glow filtering down from above, erasing their silhouette against predators looking up from below. Some use it as a burglar alarm, producing sudden bright flashes when attacked, which attract larger predators that may eat the attacker. The deep ocean is full of light, but it is a strange, purposeful light, produced by organisms for specific reasons, each flash a sentence in a language we are only beginning to decode. If you could somehow descend through the water column at night, with all your lights extinguished, you would not find darkness. You would find a world lit by living things, a world where every flicker and pulse and glow is a communication, a warning, a lure, or a disguise. The deep ocean has been this way for over 500 million years. Long before the first land animal crawled out of the shallows, long before the first forest grew, long before the first eye evolved to see the sun, there was light in the deep ocean, created not by any star, but by the chemistry of life itself. The deep ocean does not follow the rules we learn in school. Sunlight is optional. Heat comes from the earth, not the sky. Food falls from above like slow, organic snow. Light is manufactured by the animals themselves. It is a world that operates on different principles that we are still discovering and still struggling to understand. And as our understanding of the deep changes, so does our understanding of the animals that have always lived there, including the animals at the very top of the ocean's food chain, the predators whose intelligence and power are only now becoming clear. For decades, if you wanted to see the most spectacular predatory event in the ocean, you went to False Bay, South Africa. False Bay is a large, shallow inlet on the southwestern coast of the African continent, just south of Cape Town, and its waters were famous for one thing above all else. Great white sharks hunted there, not just hunted but performed. The great whites of False Bay had developed a hunting technique that was unique among sharks, and that drew researchers, filmmakers, and tourists from around the world. They launched themselves completely out of the water. The technique was called breaching, and it was as dramatic as anything in the natural world. A great white shark, weighing perhaps a ton, would dive deep beneath a colony of Cape Fur seals swimming at the surface, build speed on its ascent, and then explode out of the water in a vertical leap that could carry the entire animal 3 meters or more into the air, with a seal clamped in its jaws. The force was staggering. The visual was primal. A 3-meter predator, silhouetted against the sky, water cascading from its body. a scene that seemed to belong more to a monster movie than to the real ocean. False Bay was one of the very few places on Earth where this behaviour could be reliably observed, and it made the bay one of the most important great white shark research sites in the world. And then, starting around 2017, the great whites began disappearing. At first the absence was subtle. Researchers noticed fewer sightings. Tour operators who had built businesses around cage diving and shark spotting reported longer and longer gaps between encounters. Then the carcasses started appearing. Great white sharks, some of them large adults, were washing up on the beaches of False Bay and the surrounding coastline. They were dead, and they had been killed in a very specific way. Their livers had been removed, not torn out roughly, not bitten away in the chaos of a fight, but extracted with what researchers described as almost surgical precision. The rest of the body was often left largely intact. The liver, and sometimes the heart, was gone. The liver of a great white shark is an enormous organ. It can constitute up to a quarter of the animal's total body weight, and it is rich in squalene, a dense energy-rich oil that the shark uses for buoyancy regulation and energy storage. A large great white's liver can contain hundreds of litres of oil. It is, from a predator's perspective, the single most nutritious part of the animal, a concentrated package of calories and fat that is worth far more than the tough cartilage and muscle that makes up the rest of the body. Whatever was killing these sharks knew exactly what it wanted, and knew exactly how to get it. The culprits were identified through a combination of direct observation, acoustic tracking data, and the analysis of bite marks on the carcasses. They were orcas, specifically a pair of male orcas that researchers had been tracking for years, individuals known by their identification codes who had been sighted repeatedly in the waters around False Bay in the years leading up to the great white disappearances. Orcas, also known as killer whales, are the largest members of the dolphin family and are arguably the most intelligent and versatile predators in the ocean. They hunt in coordinated groups, communicate through complex vocalizations that are specific to their family units, and have been documented hunting everything from herring to blue whales. But what made the False Bay killings remarkable was not just that orcas were killing great white sharks, it was how they were doing it, and what effect it had on the shark's behaviour. The orcas appeared to be targeting the sharks specifically for their livers, using a technique that involved flipping the shark onto its back, which induces a state of paralysis called tonic immobility, a neurological response that many shark species exhibit when inverted. Once the shark was immobilized, the orcas could extract the liver without the shark fighting back. It was efficient, controlled, and it suggested a level of anatomical knowledge and strategic planning that went beyond simple predatory instinct. The response of the great whites was equally remarkable. They left. Not gradually, not over the course of years, but relatively quickly, as the orca predation events became more frequent. The great white shark population of False Bay essentially abandoned the area. Sightings dropped to near zero. The breaching behaviour that had made the bay famous ceased entirely. The apex predator of the ocean, an animal with a lineage stretching back over 400 million years, an animal that has survived 5 mass extinction events, encountered a predator it could not outfight and chose to flee. The ecological consequences were immediate and cascading. Without great whites to control their populations, the Cape Fur seals of False Bay increased in number and expanded their range. The seals, no longer constrained by the fear of shark predation, began feeding more heavily on fish populations that they had previously avoided. The fish populations declined. The species that depended on those fish were affected. The removal of a single apex predator from the system sent ripples through the entire food web, a phenomenon that ecologists call a trophic cascade. This pattern has been observed in other ecosystems and with other predators. When wolves were removed from the Yellowstone National Park, elk populations exploded, overgrazing riparian vegetation, which led to erosion of stream banks. which altered the flow of rivers. When sea otters were hunted nearly to extinction along the Pacific coast of North America, sea urchin populations boomed, devouring the kelp forests that provided habitat for hundreds of other species. The removal of an apex predator never affects just one species. It affects everything connected to that species, which, in a complex ecosystem, means everything. The orcas of False Bay revealed something about the ocean's power structures that science had long suspected, but rarely seen so clearly. The great white shark, the animal that popular culture has cast as the ultimate ocean predator, the fish whose silhouette alone can empty a beach, is not at the top of the food chain. The orca is. And the orca is not just physically dominant, it is strategically dominant, capable of learning new hunting techniques, transmitting those techniques to other individuals through cultural transmission, and adapting its behaviour in response to the behaviour of its prey. The orcas that killed the sharks of False Bay were not acting on instinct, they were executing a plan. The ocean's hierarchy of predation is more complex and more fluid than we typically imagine. It is not a simple ladder with one species at the top and everything else below. It is a web, a shifting dynamic network of relationships that changes with location, season, individual behaviour and circumstances. A great white shark is an apex predator in most contexts, but in the presence of orcas, it becomes prey. An orca is dominant in the open ocean, but a large pod of sperm whales, which can weigh up to 60 tons and communicate across vast distances using powerful acoustic clicks, is not an animal that any orca pod would casually approach. And in the deep ocean, in the Hadal trenches where the pressure exceeds anything at the surface, the concept of apex predation becomes almost meaningless, because the animals that live there are so different from surface life that our familiar categories of predator and prey break down entirely. The ocean is, in every sense, a world of hierarchies within hierarchies, of powers and counterpowers, of strategies and counter-strategies, all of them playing out simultaneously across millions of square miles of water, from the sunlit surface to the crushing depths. And many of these relationships are completely unknown to us, because they happen in places we cannot see, between animals we have not yet discovered, in interactions we have never observed. What we know about the ocean is a thin film of understanding stretched over an abyss of ignorance. We know the names of some of the predators, we know the outlines of some of the food webs, we know that the deep ocean is alive and that its ecosystems are complex and interconnected. But the actual day-to-day reality of life in the deep, the births and deaths and hunts and escapes and mating, displays and territorial disputes and acts of predation that occur every minute of every day in waters that no human eye has ever observed, all of that remains hidden from us. It is happening right now, as you listen to this, in the waters beneath ships and coastlines and open ocean, and it will continue happening whether we ever observe it or not. The deep ocean does not perform for human audiences. It does not arrange its mysteries for our convenience. It simply exists, ancient and indifferent and unimaginably vast, and whatever we learn about it is the result of our own effort, our own technology, our own willingness to send fragile machines and occasionally fragile human beings into conditions that are hostile to everything we are. And sometimes the ocean's mysteries are not at its bottom, but in its middle spaces, in the vast reaches of open water that seem empty from the surface, but that have accumulated more stories of disappearance and confusion and fear than any other body of water on Earth. There is a patch of the Atlantic Ocean, bounded roughly by 3 points, Miami in the south, Bermuda in the east, and Puerto Rico to the southeast, that has accumulated more stories of unexplained disappearance than any comparable area of water on the planet. The Bermuda Triangle covers approximately 500,000 square miles of ocean, a vast expanse of deep blue water crossed daily by thousands of ships and aircraft without incident. And yet, over the past century and a half, this area has become synonymous with mystery, with disappearance, with the idea that the ocean itself can reach up and swallow things, ships and planes and human beings, and leave behind nothing at all. The stories are numerous and some of them are genuinely difficult to explain. On March 4th, 1918, the USS Cyclops, a massive Navy cargo ship measuring 542 feet in length and displacing over 19,000 tons, sailed from Barbados bound for Baltimore, Maryland. She carried a crew of 306 men and a cargo of manganese ore, and she was one of the largest ships in the United States Navy. After leaving Barbados, the Cyclops was never seen again. No distress signal was received. No wreckage was ever found. No bodies were recovered. She simply vanished, along with every single person aboard, in calm seas and fair weather on a well-travelled shipping route. The Cyclops remains the single largest non-combat loss of life in United States Navy history. The Navy launched an extensive search. They found nothing. Over a century later, the wreck of the USS Cyclops has still not been located, and no definitive explanation for her disappearance has ever been established. The most common theories involve structural failure, cargo shift, or some combination of the two. Manganese ore is dense and heavy, and if the cargo shifted suddenly in the hold, it could have caused the ship to capsize so quickly that no one had time to send a distress signal. But this is speculation. The ocean took the Cyclops and kept it, and it has not returned the ship or the answer. In December 1945, 5 Navy Avenger torpedo bombers departed Fort Lauderdale, Florida, on a routine training flight known as Flight 19. The flight was led by Lieutenant Charles Taylor, an experienced pilot. The bombers flew east over the Atlantic, completed their practice bombing runs, and then turned north and west to return to base. They never arrived. Radio communications deteriorated as the flight continued, with Taylor reporting confusion about his position and difficulty with his compasses. The last transmission suggested the pilots were lost and running low on fuel. A search and rescue aircraft, a Martin Mariner flying boat with a 13-man crew, was dispatched to look for the missing bombers. The Mariner also disappeared. In total, 6 aircraft and 27 men vanished in a single day. No wreckage from any of the aircraft was ever found. These disappearances, along with dozens of others over the following decades, created the legend of the Bermuda Triangle. Books were written, documentaries were produced, theories proliferated, ranging from electromagnetic anomalies to alien abduction, to time warps, to portals, to other dimensions. The Bermuda Triangle became one of the most famous mysteries in popular culture, a place where the laws of nature seemingly broke down and the ocean swallowed things whole. The reality, according to the agencies that actually track maritime and aviation safety, is considerably less dramatic. The National Oceanic and Atmospheric Administration has stated that there is no evidence the Bermuda Triangle is any more dangerous than any other comparably sized area of ocean. The United States Coast Guard has echoed this assessment, noting that the number of incidents in the Bermuda Triangle, when adjusted for the volume of traffic passing through the area, is not statistically unusual. Ships and planes disappear in every ocean. The Bermuda Triangle simply got better publicity. That said, there are genuine physical and meteorological factors that make the area challenging for navigation. The Gulf Stream, one of the most powerful ocean currents on Earth, flows through the Bermuda Triangle, and its swift-moving waters can quickly disperse debris and wreckage, making post-accident searches extremely difficult. The area is prone to sudden violent weather events, including waterspouts and the powerful thunderstorms that develop along the boundary between the warm Gulf Stream and cooler Atlantic waters. Some researchers have proposed that eruptions of methane gas from deposits on the ocean floor could theoretically reduce the density of water enough to cause a ship to lose buoyancy and sink rapidly, although this hypothesis remains unproven and controversial. And there is the matter of compass variation. The Bermuda Triangle is one of the few places on Earth where true north and magnetic north align, which can cause navigational confusion for crews accustomed to applying a correction factor, a small technical detail that could, in some circumstances, contribute to disorientation. None of these explanations are supernatural. All of them are ordinary physical phenomena that operate everywhere in the ocean to varying degrees. The Bermuda Triangle is not a portal to another dimension. It is a patch of ocean where storms are common, currents are strong, traffic is heavy, and the water is very, very deep. When things go wrong in the deep water, they tend to stay gone. On the other side of the world, in the western Pacific Ocean, there is another area with a similar reputation. The Devil's Sea, sometimes called the Dragon's Triangle, stretches roughly from Japan south to the Mariana Islands and east toward the Bonin Islands. Like the Bermuda Triangle, the Devil's Sea has been associated with reports of ships and aircraft disappearing under mysterious circumstances. Japanese legend holds that the area is inhabited by dragons that pull ships beneath the waves. In the 1950s, several Japanese research vessels were reportedly lost while investigating the area, though the details of these losses are disputed and the documentation is incomplete. The Devil's Sea is a genuinely dangerous body of water, but the dangers are geological and meteorological rather than supernatural. The area sits along the Pacific Ring of Fire, a zone of intense tectonic and volcanic activity that produces frequent earthquakes, underwater eruptions, and the sudden formation of volcanic islands that can appear and disappear over relatively short time frames. The weather in the western Pacific is volatile, with typhoons capable of generating waves that can overwhelm even large vessels, and the waters are deep, with the Mariana Trench itself running through the heart of the region, ensuring that anything that sinks will fall to depths where recovery is effectively impossible. There is a third body of water that, while less famous than the Bermuda Triangle or the Devil's Sea, is in many ways more genuinely strange. The Sargasso Sea is located in the North Atlantic, bounded not by coastlines but by 4 ocean currents: the Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south. These currents rotate clockwise around the Sargasso Sea, creating a vast, relatively calm body of water that is the only sea on Earth defined entirely by ocean currents rather than land boundaries. Within this sea, enormous mats of free-floating sargassum seaweed drift on the surface, sometimes accumulating in dense patches that can stretch for miles. The Sargasso Sea has inspired its own mythology. Sailors in the Age of Sail told stories of ships becoming trapped in the weed, their hulls encrusted with barnacles and algae, their crews starving as they drifted endlessly in the becalmed waters. While these stories are largely exaggerated, the Sargasso Sea is a genuinely unusual place. Its ecosystem is distinct from the surrounding Atlantic, supporting unique species that are found nowhere else. The European eel, which has mystified biologists for centuries, makes its way to the Sargasso Sea to spawn, travelling thousands of miles from European rivers to a specific area of the Atlantic to breed, and then presumably to die. No one has ever observed European eels mating in the wild. No one has ever found a spawning aggregation. The eels simply arrive in the Sargasso Sea, and new larvae appear, and then the larvae ride the ocean currents back to Europe, where they enter rivers and grow to adulthood, and eventually, when the time comes, make the impossible journey back across the Atlantic to breed. How they navigate this route, how they know when to leave, how they find the Sargasso Sea across thousands of miles of open ocean, these are questions that remain largely unanswered after more than a century of research. The Sargasso Sea is also remarkable for what it does not have. Despite being in the middle of the North Atlantic, one of the most heavily trafficked ocean basins on Earth, the Sargasso Sea is relatively calm and clear. Its waters are among the clearest in the world, with visibility extending to depths of over 60 meters. It is an oasis of stillness in a busy ocean, a place where the currents swirl inward and the water barely moves, where things that drift in have a tendency to stay. The ghost ships of the ocean are not supernatural phenomena. They are the result of storms and structural failures and navigational errors and human mistakes, ordinary tragedies made extraordinary by the ocean's ability to remove evidence. When a ship sinks in deep water, The wreckage settles on the seafloor miles below the surface, out of reach of salvage operations, out of reach of investigation, out of reach of closure. The families of the crew are left with nothing but silence and uncertainty. The ship's log and its records go down with it. The story of what happened in its final hours is known only to the ocean and to the dead. There are an estimated 3 million shipwrecks scattered across the world's ocean floors. Most of them will never be found. Most of them will never be identified. They are the unwritten chapters of maritime history, resting in the dark. Their stories told only by the slow accumulation of sediment and the creatures that make homes in their decaying hulls. The ocean does not collect mysteries deliberately. It is not malevolent. It is not cursed. It is simply vast and deep and dark, and it operates on timescales and pressures that are fundamentally incompatible with human fragility. We are surface creatures, adapted for air and light and stable ground beneath our feet. The ocean is none of those things, and when we venture onto it or into it, we are visitors in a world that does not accommodate visitors. The stories of the Bermuda Triangle and the Devil's Sea and the Sargasso Sea are not stories about supernatural forces. They are stories about the limits of human knowledge and human technology in the face of the ocean's indifference. They are reminders that the sea does not respect our schedules, our expectations, or our lives. It simply is. And it has been, and it will continue to be, long after the last ship has sailed and the last plane has flown. And beneath all of these surface waters, beneath the shipping lanes and the storm tracks and the currents that carry weed and wreckage and larvae across entire ocean basins, there is the seafloor itself, a vast, largely unmapped landscape of mountains and plains and canyons and trenches that holds more unknowns than any other surface on the planet. We have been trying to map it for over a century, and we are still less than a third of the way done. In 1872, when the HMS Challenger set out on her pioneering voyage, the method for measuring the depth of the ocean was remarkably crude. You tied a weight to a rope, lowered it over the side and waited for it to hit the bottom. Then you pulled it back up and measured the rope. The process could take hours for a single sounding, and the results were imprecise, affected by currents that pushed the rope sideways and by the difficulty of determining exactly when the weight had reached the seafloor, rather than simply becoming snagged on some intermediate obstruction. The Challenger expedition took soundings at 362 stations around the world over the course of 3.5 years, and the resulting map, while groundbreaking at the time, was little more than a connect-the-dots sketch of a landscape that covered more than 360 million square kilometres. A century and a half later, we have satellites that can measure the height of the ocean's surface with centimetre precision, and from those surface measurements, scientists can infer the general topography of the seafloor below. Where the seafloor has a large mountain, the gravitational pull of that mountain draws water slightly toward it, creating a barely detectable bulge on the ocean's surface. Where there is a trench, the reduced gravitational pull creates a slight depression. By measuring these minuscule variations in sea surface height from orbit, scientists have been able to produce maps that show the broad features of the ocean floor, the major ridges and trenches and basins that define its geography. But these satellite-derived maps are, in the language of cartography, low resolution. They can show features larger than about 5 kilometres across, but anything smaller than that is invisible. A sea mount 2 kilometres tall and 3 kilometres wide, a feature larger than many mountains on land, would not appear on a satellite-derived bathymetric map. An entire volcanic peak could be missing from our charts, and we would not know it was there until a ship sailed over it and happened to be running its depth sounder at the time. To map the ocean floor in the true detail, you need to send sound into the water. Multibeam, echo sounders mounted on the hulls of ships emit fans of acoustic pulses that spread outward as they descend, bouncing off the seafloor and returning to the ship. By measuring the time it takes for each pulse to return and the angle at which it arrives, computers can construct a detailed three-dimensional image of the bottom. This is how the ocean floor is being mapped by the Seabed 2030 project, an international effort launched in 2017 with the goal of producing a complete, high-resolution map of the entire ocean floor by the end of this decade. As of June 2024, just 26.1% of the ocean floor had been mapped to modern standards. That means nearly 3/4 of the bottom of our planet remains, in practical terms, unknown territory. The scale of what remains unmapped is difficult to comprehend. The Pacific Ocean alone covers approximately 165 million square kilometres, and much of its abyssal floor has never been surveyed by any ship. The Southern Ocean, surrounding Antarctica, is even less explored, its remote location and violent weather making survey operations dangerous and expensive. Even in relatively well-travelled waters like the North Atlantic, there are enormous areas of seafloor that have been seen only in the blurred approximation of satellite data. What we keep finding, every time we do map a new section, is that the ocean floor is far more complex and varied than the satellite data suggested. Seamounts, underwater mountains that rise at least 1,000 metres from the surrounding seafloor, are vastly more numerous than previously estimated. Early surveys suggested there might be about 30,000 seamounts in the world's oceans. More recent estimates, based on improved satellite data and targeted ship surveys, place the number at over 100,000, and some researchers believe the true count could be significantly higher. Each seamount is a potential island of biodiversity, an elevated platform where ocean currents are deflected upward, bringing nutrients from the deep and creating conditions that support unusually rich communities of fish, corals, sponges, and other marine life. Many of these seamounts have never been visited by any human or robotic explorer. Their ecosystems are completely unknown. The ocean floor is also littered with the evidence of volcanic activity on a scale that dwarfs anything on the surface. The mid-ocean ridge system, where tectonic plates pull apart and new oceanic crust is formed from molten rock rising from the Earth's mantle, is the single largest geological feature on the planet, a continuous chain of underwater mountains stretching approximately 65,000 kilometres through every ocean basin. Along this ridge, volcanic eruptions occur regularly, building new rock and reshaping the seafloor in processes that have been going on for billions of years. In August 2023, 3 previously unknown underwater volcanoes were discovered off the coast of Sicily, in the Mediterranean Sea, a body of water that has been sailed by human beings for at least 10,000 years. If we are still finding volcanoes in the Mediterranean, imagine what remains undiscovered in the vast unsurveyed reaches of the Pacific and Southern Oceans. Some of the volcanic features on the ocean floor are genuinely unlike anything found on land. In the Mariana Trench, researchers have documented a pool of molten sulfur on the seafloor, a shimmering liquid lake of volcanic material sitting at the bottom of a submarine volcanic crater. Molten sulfur has a melting point of about 115 degrees Celsius, and this pool is kept liquid by the volcanic heat emanating from the Earth's crust below. It is, as far as anyone knows, the only place on Earth where this phenomenon has been observed. A lake of liquid sulfur sitting at the bottom of the ocean in a trench deeper than any mountain is tall. If you described it in a science fiction novel, readers would accuse you of making it up. The exploration of the ocean floor has also produced some of the most sophisticated and creative scientific investigations ever attempted. In December 2014, a team of researchers aboard the Schmidt Ocean Institute's research vessel, Falkor, travelled to the Challenger Deep to study the acoustic properties of the deepest ocean. They deployed 2 free-falling instrument platforms, each containing a glass sphere designed to implode at a specific depth. The plan was to use the implosion as a calibrated sound source, a known event at a known depth, and then measure how the sound propagated through the water column to calculate the precise depth of the Challenger Deep with greater accuracy than previous methods had achieved. One of the glass spheres imploded at a depth of approximately 8,500 metres, shattering under the pressure and sending a shock wave radiating outward through the water. The shock wave bounced off the seafloor, off the ocean's surface and off the walls of the trench, creating multiple echoes that the remaining instruments recorded with extraordinary precision. By analysing the arrival times of these echoes and applying sophisticated acoustic models, the researchers were able to calculate the depth of the Challenger Deep as 10,983 metres, plus or minus 6 metres. This was one of the most constrained and precise depth measurements ever made, and it was achieved in part by deliberately destroying an instrument and listening to the sound of its death. The ocean floor is also an archaeological treasure of almost incomprehensible scope. There are an estimated 4 million shipwrecks on the sea floor worldwide, though some estimates place the number even higher. In the Gulf of Mexico alone, researchers believe there are more than 4,000 wrecks scattered across the sea floor from the shallows of the continental shelf to the deep abyssal plains. Most of these wrecks have never been located. Most will never be identified. They range from ancient trading vessels to modern cargo ships, from wooden sailing boats to steel-hulled warships, from pleasure yachts to submarines, each one a time capsule preserving a moment of maritime history in the dark, preserving conditions of the ocean bottom. In 2019, a sonar survey in the Gulf of Mexico detected a previously unknown shipwreck at a depth that made visual identification possible, but physical recovery impractical. When researchers sent a remotely operated vehicle to investigate, the live video feed revealed a 19th century sailing vessel, approximately 124 feet long, constructed of wood and copper sheathing. The ship's structure was remarkably well preserved, the cold, low oxygen conditions of the deep Gulf acting as a natural preservative, but the ship's identity was a mystery. Its country of origin was unknown. The number of crew members it had carried was unknown. Its purpose, whether it was a merchant vessel or a warship or something else entirely, was unknown. And the circumstances of its sinking, whether it was storm or fire or collision or some other catastrophe, were unknown. The ship sat on the seafloor, anonymous and silent, its story lost to the water in the centuries. This is the paradox of the ocean floor. It preserves things beautifully, the cold temperatures and low oxygen and high pressure slowing the processes of decay and degradation that would quickly destroy the same objects on land. A wooden ship that would rot away in decades on the surface can persist for centuries on the deep sea floor. A body that would decompose in weeks in warm air can be preserved, or at least its skeletal remains can be preserved for far longer in the cold depths. The ocean is an extraordinary archive, a natural museum that contains more artifacts and more history than all the museums on land combined. But it is a museum with no catalogue, no index, no map, and no lights. The exhibits are scattered across 360 million square kilometres of floor space, in rooms where the pressure will kill you, and the darkness is absolute. We are mapping this floor as fast as our technology and funding allow. The Seabed 2030 project represents an unprecedented international cooperation, with research vessels from dozens of countries contributing survey data to a shared global database. Autonomous underwater vehicles, robotic submarines that can operate without human pilots, are being developed and deployed to map areas that are too deep or too dangerous for conventional survey ships. Satellite technology is improving, offering slightly better resolution with each new generation of instruments, but the ocean is vast, and progress is measured in fractions of a % per year. At current rates, the goal of mapping the entire ocean floor by 2030 is ambitious, perhaps unrealistically so, but even partial completion will reveal more about the planet's geography in a few years than all previous centuries of exploration combined. Every new survey produces surprises. Underwater canyons deeper than the Grand Canyon, volcanic features that reshape our understanding of the Earth's internal processes, ecosystems that exist in isolation, cut off from the rest of the ocean by ridges and currents, evolving independently for millions of years, shipwrecks that rewrite maritime history, geological formations that challenge existing theories. The ocean floor is not a monotonous wasteland of mud and rock. It is as varied and dramatic as any landscape on the surface, more so in many ways because it has been shaped by forces that operate on scales and timelines that dwarf anything in the human experience, and in the most remote corners of the ocean floor, in places that have been cut off from the rest of the world by ice for decades or centuries, new discoveries are being made that challenge even our expanded understanding of where and how life can exist. There are places on the ocean floor where the very ground is opening up, where ice that has covered the seabed for longer than any human civilization has existed is retreating, revealing surfaces that have not been exposed to the ocean in hundreds or thousands of years. And when scientists get to these newly uncovered places, when they send their cameras and their robots down to see what lies beneath the vanished ice, they find life. Not the scarred, empty landscapes you might expect after centuries of burial beneath a frozen sheet, but living communities, organisms that were apparently thriving under the ice, growing in the dark, sustained by processes we are only beginning to understand. The ice is revealing its secrets, and the ocean, as always, is more alive than we ever imagined. On January 13th, 2025, an iceberg the size of the city of Chicago broke away from the George VI ice shelf in Antarctica. The calving event was not unexpected. Scientists had been monitoring the ice shelf for years, watching as warming ocean temperatures weakened the ice from below, and surface melting weakened it from above. The process is slow by human standards, but rapid by geological ones, and when the break finally came, it exposed a section of seafloor that had been covered by ice for decades, possibly centuries, possibly longer. The seabed beneath an ice shelf is one of the most inaccessible environments on Earth, shielded from the ocean above by a thick ceiling of ice, cut off from sunlight, cut off from the normal circulation of nutrients and organic material that sustains life in the open ocean. When the ice disappears, researchers have a brief window, sometimes only weeks or months before new ice forms or icebergs drift over the area, to see what was living underneath. The Schmidt Ocean Institute, which operates the research vessel Fulcor 2, mobilized rapidly. The team sailed to the site of the calving event and deployed remotely operated vehicles to survey the newly exposed seafloor. What they found, at a depth of nearly 230 meters, was not the barren, lifeless expanse that some models had predicted. Instead, the cameras revealed thriving biological communities. Large sponges, some of them clearly very old, clung to the rocky substrate. Clusters of anemones spread across the seabed in colourful aggregations. Other organisms, less immediately identifiable, populated the crevices and ledges of the underlying rock. The sponges were particularly significant. Marine sponges are among the slowest growing organisms on Earth. Some species add less than 2 centimeters to their size per year. The sponges found beneath the former ice shelf were not small. Their size suggested they had been growing for decades, possibly hundreds of years, which meant that this community had been active and alive under the ice for a very long time. Life had not merely survived beneath the ice shelf, it had established itself, grown, and persisted in conditions of total darkness, near freezing temperatures and complete isolation from the productive surface waters above. How these organisms sustain themselves is not entirely clear. Without sunlight, photosynthesis is impossible, so the base of the food chain beneath an ice shelf must be something else. The most likely candidates are chemosynthetic bacteria, similar to those found at hydrothermal vents, that derive energy from chemical reactions in the rock and sediment, and the slow, steady rain of organic particles that may filter beneath the ice shelf from the open ocean at its margins. But the details of under-ice shelf ecology are poorly understood, because so few such ecosystems have ever been observed. Each time an ice shelf collapses, it is both a loss, the destruction of a unique environment, and an opportunity, a chance to study life in conditions that are otherwise impossible to access. The Antarctic discoveries did not stop at the ice shelf. Thousands of miles to the north, off the coast of Argentina, the same Schmidt Ocean Institute expedition explored a feature of the ocean floor that had never been surveyed in detail. The Argentine Canyon, located in the South Atlantic, is a submarine canyon, that plunges to depths of more than 6,000 meters, making it roughly twice as deep as the Grand Canyon. It is carved into the continental slope off the coast of Patagonia, and at its base 2 major ocean currents converge. One current flows south from the tropics, carrying warm salty water. The other flows north from Antarctica, carrying cold, nutrient-rich water. Where these 2 currents meet, they create conditions of extraordinary biological productivity, a mixing zone where nutrients from both tropical and polar sources are available, supporting an ecosystem of remarkable diversity and beauty. When the remotely operated vehicles descended into the Argentine Canyon, the video feeds revealed a world of unexpected colour. Many of the deep-sea organisms appeared in shades of peach pink and orange, vivid hues that seemed out of place in an environment of perpetual darkness. The explanation is a masterpiece of evolutionary adaptation. Red light does not penetrate deep water. It is absorbed within the first few hundred meters, which means that at depth, the colour red is effectively invisible. An animal that is red or orange or pink in the deep ocean is, for all practical purposes, wearing camouflage. It is invisible to any predator or prey whose eyes are adapted to the blue and green wavelengths that dominate the deep. The beauty that the cameras captured was not decorative, it was functional. Each splash of colour was a survival strategy, refined over millions of years of evolution in the dark. Among the creatures filmed in the Argentine Canyon was a translucent telescope octopus, an animal so strange that the scientists who observed it struggled to describe what they were seeing. The telescope octopus, Amphitretus pelagicus, is a small, gelatinous deep-sea cephalopod with large tubular forward-facing eyes that give it an almost comical appearance. The animal was filmed floating upside down, its body nearly transparent, its internal organs faintly visible through its skin. It drifted through the dark water with a slow, dreamlike motion, seemingly unconcerned by the presence of the ROV and its lights. The telescope octopus is rarely seen. It lives in the mesopelagic and bathypelagic zones, between about 200 and 2,000 meters, and it is one of the many deep-sea species that is known primarily from a handful of observations scattered across decades of sporadic deep-sea exploration. The Argentine Canyon expedition also documented siphonophores, colonial organisms that are among the most extraordinary life forms in the ocean. A siphonophore is not a single animal, but a colony of specialized individuals called zooids, each performing a specific function, some responsible for swimming, some for feeding, some for reproduction, some for defense. The colony operates as a single organism, coordinated by chemical and neurological signals that pass between the zooids. Some siphonophores are among the longest animals in the ocean. The giant siphonophore Praia do Baia can reach lengths of 40 to 50 meters, longer than a blue whale, making it one of the longest animals ever to live on Earth. And yet, because it is fragile and translucent and lives in the deep water column, it is almost never seen and is poorly understood. The deep ocean is full of creatures like this, animals that are enormous or beautiful or bizarre or all three, animals that have been living in the deep for millions of years and that we have seen only in fleeting glimpses, in the brief moments when a camera or a submersible happens to pass through their territory. For every deep-sea species that has been formally described and catalogued, there are likely dozens more that exist only as blurry images in a researcher's video files, or as unnamed specimens in a museum collection, or as animals that have never been seen at all, known only from traces of DNA filtered from seawater. The concept of environmental DNA, or eDNA, has become one of the most important tools in modern ocean research. Every organism that lives in the ocean sheds traces of itself into the water, fragments of skin and scales and mucus and waste that carry DNA. By collecting water samples and analysing the DNA they contain, researchers can detect the presence of species without ever seeing them. It is like reading footprints in snow, except the footprints are molecular and the snow is the entire ocean. eDNA surveys have revealed the presence of species in areas where they were not expected. confirmed the existence of rare animals that have not been observed directly in years, and suggested the presence of organisms that may not yet have been formally described by science. The ocean is telling us what lives in it. We just need to learn to read the messages. At approximately 1,550 meters below the surface in the waters off the California coast, researchers from the Monterey Bay Aquarium Research Institute have been occasionally encountering one of the most enigmatic creatures in the deep sea for over 20 years. Baphidivius caudactylus is a small gelatinous animal, a type of sea slug that hovers in the water column with a wide paddle-like tail from which several finger-like projections, called dactyls, extend. The animal uses a hood-like structure surrounding its head to capture prey, enveloping small organisms in a gelatinous trap. It has detachable tentacles, which it can apparently jettison when threatened, leaving them behind as decoys while the animal escapes. Despite more than 2 decades of occasional sightings, almost nothing is known about this creature's biology. How does it reproduce? How long does it live? What is the function of the dactyls on its tail? Are they sensory organs, defensive structures, or something else entirely? How many of them exist? Where else in the ocean do they live? These questions remain unanswered, not because the animal is uninteresting, but because it lives at a depth that makes sustained observation extraordinarily difficult. Each sighting is a brief, chance encounter, a few minutes of video footage captured during an ROV dive that was probably looking for something else entirely. The deep ocean reveals its inhabitants on its own schedule, in its own way, and no amount of human planning can guarantee a sighting of any particular species on any particular dive. This is the fundamental challenge of deep-sea biology. The organisms are there. We know they are there. We can see evidence of them in eDNA samples, in the remains found in the stomachs of deep-diving whales and fish, in the occasional specimens that wash up on beaches, or are caught in deep-water fishing operations. But seeing them in their natural environment, observing their behaviour, understanding their ecology, all of this requires us to be in the right place at the right time with the right equipment, in an ocean that covers 360 million square kilometres, and that we have explored only in tiny disconnected fragments. The deep ocean is not a single environment. It is thousands of environments, each with its own conditions, its own chemistry, its own community of organisms. A hydrothermal vent on the mid-Atlantic ridge supports a completely different ecosystem from a vent in the eastern Pacific. The sea floor of the Arctic Ocean harbours species that are found nowhere in the tropics. The Hadal Trenches, each one isolated from the others by vast stretches of shallower water, have evolved their own unique fauna, populations of amphipods and snailfish and bacteria that are found in one trench and no other. The deep ocean is not one world. It is many worlds, separated by barriers of depth and distance and chemistry, each one evolving independently, each one containing secrets that the others do not share. And perhaps the most unsettling aspect of the deep ocean's mysteries is not what we have found, but what we know we have not found. The estimates of total marine biodiversity suggest that roughly 2 million species inhabit the world's oceans. Only a fraction of those, perhaps 240,000, have been formally described. The rest are out there, unnamed and undocumented, living their lives in the dark. Some of them are small, microscopic organisms that would require electron microscopes to see. Some of them are large, perhaps very large, animals that live at depths we have rarely visited. The 2024 expedition off Chile found more than 100 new species in a single survey. The 2025 Ocean Species Discoveries Initiative described 14 new species from depths exceeding 6,000 meters, including organisms so strange that researchers had to create entirely new taxonomic categories to accommodate them. Every expedition to the deep ocean finds something new. Not sometimes. Every time. This has been true since the HMS Challenger first lowered its nets into the abyss in 1873, and it remains true in 2026. The deep ocean has been producing new species, new mysteries and new questions faster than we can answer the old ones for as long as we have been looking. There is no sign that this pace is slowing. If anything, as our technology improves and our explorations become more systematic, the rate of discovery is accelerating. The ocean beneath the ice, the ocean in the canyons, the ocean at the vents, the ocean in the trenches, all of it is alive, all of it is complex, all of it is old beyond human reckoning, and most of it has never been seen by human eyes. We are explorers standing at the edge of a continent we have barely entered, mapping its coastline, catching glimpses of its interior, and knowing with absolute certainty that the interior is vaster and stranger and more beautiful than anything we have yet imagined. The question that sits at the centre of all deep-sea research, the question that drives every expedition and funds every submersible, and motivates every graduate student who spends years studying organisms that almost nobody will ever hear of, is simple. What else is down there? And the honest answer, the answer that every oceanographer will give you if you ask them late at night after a long day at sea, is this: we do not know. We genuinely do not know. And that is both the most humbling and the most exciting thing about the ocean. It is the last great unknown on our planet, the one place where discovery is not just possible but guaranteed, the one place where the question, what else is down there, will always have an answer we did not expect. The darkness down there is patient. It has been waiting for 4 billion years. It can wait a little longer. But for now, for tonight, we have gone deep enough. We have descended through the zones of light and twilight, and midnight and abyss. We have listened to the sounds the ocean makes when it thinks no one is listening. We have traced the paths of ships and submarines that sailed into the dark and never returned. We have met creatures that defy our understanding of size and age and the limits of biology. We have walked the floor of the deepest trench and stood at the edge of underwater canyons that dwarf anything on the surface. We have seen life where we expected lifelessness, heard sounds where we expected silence, and found complexity where we expected simplicity. It is time now to begin the long ascent, to rise back through the layers of the ocean, through the crushing pressure and the freezing cold and the absolute darkness, back toward the light, back toward the surface, back toward the world you know. There is a phenomenon in the deep ocean that scientists call a whale fall. When a great whale dies, whether from old age or illness or predation, or the slow accumulation of toxins in its body, its carcass sinks. The descent is slow. A whale's body, even in death, retains enough buoyancy to delay the inevitable, and it may take hours or days for the carcass to settle on the seafloor, drifting through the zones of the ocean like a slow, massive shadow passing through the water column. But eventually, gravity wins, as it always does, and the whale comes to rest on the bottom. What happens next is one of the most extraordinary ecological events in the deep ocean. A dead whale, depending on its species, can weigh anywhere from 20 to 150 tons. In the nutrient-poor, abyssal environment, where food is scarce and organisms subsist on the thin, slow rain of organic particles from above, a whale fall is a bonanza of almost unimaginable proportions. It is the equivalent of an entire ecosystem suddenly materializing on the desert floor, a concentrated source of nutrition that will sustain a succession of communities for decades. The first to arrive are the mobile scavengers, hagfish and sleeper sharks and rat-tail fish and amphipods, drawn from miles around by the chemical plume of decomposition that spreads through the water. These animals feed on the soft tissues, the blubber and the muscle and the organs, stripping the carcass of its most accessible nutrition in a feeding frenzy that can last for months. A single whale fall can attract hundreds or thousands of scavengers, creating a temporary oasis of activity on an otherwise barren seafloor. As the soft tissues are consumed, a second community takes over. Polychaete worms and crustaceans colonize the remaining tissue in the exposed bones, feeding on the organic material that the scavengers left behind. This phase can last for years, as the slower-feeding organisms gradually reduce the carcass to a skeleton. The third and longest phase begins when the bones themselves become the resource. Whale bones are rich in lipids, oils that are stored in the porous interior of the skeleton, and these lipids can sustain specialized organisms for decades. One of the most remarkable of these organisms is a genus of worm called Osedax, whose name means bone devourer. Osedax worms have no mouth, no stomach, and no digestive system. Instead, they bore into the bone using root-like structures and harbour symbiotic bacteria that break down the lipids and provide the worm with nutrition. They are bone-eating worms that rely on bacteria to do the actual eating, a partnership that allows them to exploit a food source that no other animal can access. A whale fall can sustain a community of organisms for 50 to 100 years. In the deep ocean, where individual organisms grow slowly and live a long time, a single whale carcass can be the foundation of a self-sustaining ecosystem that persists for longer than a human lifetime. And because whales have been dying and sinking for tens of millions of years, the deep ocean floor is dotted with whale falls at various stages of decomposition, each one a small island of abundance in the vast desert of the abyss, each one supporting a unique community of organisms that exist nowhere else. Some of the species found at whale falls are found only at whale falls. They have evolved specifically to exploit this resource, and they survive by dispersing their larvae through the deep water, drifting on the slow currents until they encounter the chemical signal of another dead whale settling on the seafloor. The larvae may drift for months or years before finding a new whale fall, and many of them never do, but enough survive to maintain the population, and the cycle continues, whale by whale, fall by fall, across the deep ocean floor. The whale fall is a reminder that death in the ocean is not an ending, it is a transformation. The nutrients that were part of the whale's body when it was alive, the carbon and nitrogen and phosphorus and calcium that had accumulated over decades of feeding at the surface, are returned to the deep ocean ecosystem, recycled through the bodies of scavengers and worms and bacteria, and eventually dispersed into the sediment, where they become part of the geological record. The whale's death feeds the deep for decades. Its nutrients endure for millennia. Nothing is wasted. Nothing is lost. Everything is transformed. This principle operates at every scale in the ocean. The marine snow that feeds the abyssal fauna is composed of dead plankton, fecal pellets, shed mucus, and other organic detritus from the surface waters. It is the waste and the death of the productive surface ecosystem, falling continuously through the water column, feeding the organisms below. The deep ocean lives on the leavings of the shallow ocean, and the shallow ocean, in turn, depends on the nutrients that are recycled from the deep, through upwelling currents and volcanic activity. The ocean is a closed system, or very nearly so, a vast recycling engine that has been converting chemistry into biology and biology back into chemistry for 4 billion years. The currents that drive this recycling are themselves one of the ocean's great mysteries, or rather, one of its great complexities. The ocean circulation is driven by differences in temperature and salinity, a system called thermohaline circulation that operates on timescales of centuries to millennia. Warm salty water at the surface of the tropical Atlantic cools as it flows northward, becoming denser, and eventually sinks to the bottom near Greenland and Iceland. This cold, dense water then flows southward along the floor of the Atlantic, eventually reaching the Southern Ocean, where it joins the Antarctic circumpolar current and is distributed to the Indian and Pacific Oceans. Over the course of approximately 1,000 years, this deep water gradually warms, rises back to the surface and flows northward again, completing a circuit that oceanographers call the global conveyor belt. The conveyor belt moves more water than all the rivers on Earth combined. It is the single most important mechanism for distributing heat around the planet, and it plays a critical role in regulating Earth's climate. Changes in the conveyor belt, caused by alterations in the temperature or salinity at the surface, can have profound effects on weather patterns, sea levels and marine ecosystems thousands of miles from the point where the change occurred. The Little Ice Age, which cooled Europe for several centuries starting around 1300, may have been triggered in part by a slowdown in the Atlantic thermohaline circulation. The abrupt climate shifts that punctuated the last ice age, sudden warmings and coolings of 10 degrees Celsius or more over the course of a few decades, are thought to have been caused by reorganizations of the conveyor belt, triggered by massive influxes of fresh water from melting ice sheets. The deep ocean is not static. It moves, slowly, ponderously, on time scales that make human history look like a heartbeat, but it moves. The water at the bottom of the Pacific Ocean right now left the surface near Greenland approximately 1,000 years ago. It has been travelling through the deep, in the cold and the dark for 10 centuries. It passed the Azores and the Equator and the Cape of Good Hope and the Southern Ocean and the Mariana Trench, all of it in darkness, all of it at near freezing temperatures, all of it under enormous pressure, carrying with it the dissolved oxygen and carbon dioxide and nutrients that were present in the surface waters of the North Atlantic when it sank. That water is ancient by human standards. By ocean standards, it is just one more circuit of the endless, slow, planetary rhythm of circulation. The deep scattering layer, that vast dense concentration of marine organisms that rises and falls with the cycle of day and night, is intimately connected to this circulation. The animals in the deep scattering layer, the small fish and squid and crustaceans and gelatinous organisms that make up this living cloud, feed at the surface at night and retreat to the deep during the day. In doing so, they transport carbon from the surface to the deep, in the form of their bodies and their fecal pellets and the organic material they carry downward. This biological pump, as it is called, is one of the most important mechanisms for removing carbon dioxide from the atmosphere and storing it in the deep ocean, a process that has significant implications for Earth's climate and that is only beginning to be fully understood. The deep scattering layer was first detected during World War II, when Navy sonar operators noticed a persistent false bottom on their screens, a layer that appeared to be the seafloor but that moved up and down with the time of day. At first it was thought to be a technical error or an unusual acoustic phenomenon. It took years of investigation to determine that the false bottom was actually a dense layer of living organisms, so concentrated that it reflected sonar signals back to the ship. The deep scattering layer is visible on sonar in every ocean on Earth. It is one of the most prominent biological features on the planet, and hardly anyone has heard of it. At night, when the layer rises, the surface waters come alive with activity. Small fish and squid and krill ascend from the deep to feed on the phytoplankton and zooplankton that accumulate near the surface during the day. Predators follow them up, and predators of predators follow those, creating a vertical food chain that extends from the surface to the deep. This nightly migration involves billions of individual organisms, a biomass so large that it shows up on satellite measurements of ocean colour and productivity. It is by any measure the largest animal migration on Earth, and it happens every single night in every ocean and has been happening for hundreds of millions of years. The ocean at night is a place of extraordinary activity. The surface may look calm, the water may look dark, but beneath the surface the vertical migration is underway. The currents are flowing, the vents are erupting, the bioluminescence is firing, the whales are singing, the squid are hunting, and the slow, ancient rhythm of the deep is continuing as it has continued since long before anyone was there to notice it. This is the world beneath the waves, a world that does not sleep, that does not rest, that does not pause, a world that continues whether we are watching or not, whether we understand it or not, whether we are awake or asleep. And now, at last, it is time for you to rest. The ocean will continue without you. It always has. It always will. There is one more thing I want to tell you before we begin the long, slow return to the surface. It is about the blue whale, the largest animal that has ever lived on Earth, and the mystery that still surrounds it. The blue whale can reach 30 meters in length. It can weigh over 170 tons. Its heart is the size of a small car. Its tongue alone weighs as much as an elephant. Its arteries are wide enough for a human child to crawl through. It is by every metric of size that biology has ever produced the largest creature to have ever existed on this planet, larger than the largest dinosaurs, larger than the largest marine reptiles, larger than anything that evolution has produced in 4 billion years of experimentation. And yet, for an animal of this size, the blue whale is astonishingly elusive. The commercial whaling industry hunted blue whales to the brink of extinction during the 20th century, reducing a global population of perhaps 350,000 to fewer than 10,000. The International Whaling Commission banned the hunting of blue whales in 1966, and since then the population has recovered somewhat, but they remain endangered and they remain rare. Their low numbers and their vast oceanic ranges make them extraordinarily difficult to study. We do not know how long they live, although estimates suggest a lifespan of 80 to 90 years or more. We do not know the full extent of their migrations, although they are known to travel thousands of miles between feeding grounds and breeding areas. And we do not fully understand their songs. Blue whales produce some of the loudest sounds in the animal kingdom, low-frequency calls that can exceed 180 decibels and travel across entire ocean basins. These calls are below the range of human hearing, infrasonic rumbles that vibrate through the water at frequencies between 10 and 40 hertz. A blue whale calling in the Pacific can, under the right conditions, be heard by another blue whale on the other side of the ocean. The calls are thought to serve multiple functions, including mating, navigation, and possibly the acoustic mapping of underwater topography. But much about blue whale communication remains unknown, including the exact meaning of specific call types and the degree to which individual whales can be identified by their voices. In 2017, a video filmed off the coast of Sri Lanka captured blue whale behaviour that had never been documented before. 2 blue whales were filmed rolling and racing through the water in what appeared to be a social interaction, possibly a mating display. The footage was controversial among experts, with some interpreting it as courtship and others arguing that it might be play behaviour or even aggression. The disagreement highlighted how little we know about the private lives of these animals. The largest creature on Earth, an animal that has existed in something close to its current form for millions of years, and we cannot agree on what it is doing when we see it doing something new. The ocean keeps its largest secrets in the bodies of its largest inhabitants, and even when those inhabitants surface to breathe, even when we point cameras at them and track them with satellites and listen to their songs with hydrophones, the fundamental mystery of their existence remains intact. The ocean's memory is longer than ours. The sediment on the sea floor records the history of the planet in layers, each one a chapter in a story that stretches back billions of years. The oldest oceanic crust, found at the margins of the Pacific Plate, where it is being subducted beneath other plates, is approximately 200 million years old. But the sediment that covers it, the slow accumulation of organic and inorganic particles that have been falling through the water column for eons, contains a record of life and climate and chemistry that extends far beyond the age of the rock beneath it. By drilling into the seafloor and extracting cores of sediment, scientists can read the ocean's memory, layer by layer, tracing changes in temperature and salinity and biological productivity over millions of years. These sediment cores contain the shells of microscopic organisms called foraminifera, single-celled creatures that build shells of calcium carbonate and live in the surface waters of the ocean. When they die, the shells sink to the bottom and accumulate in the sediment, and the chemical composition of those shells records the temperature and chemistry of the water in which they lived. By analysing the ratios of oxygen isotopes in foraminifera shells, scientists have reconstructed the temperature history of the ocean over the past 100 million years, producing a record of climate change that is among the most detailed and reliable in all of Earth science. This record tells us that the ocean has been through periods of warmth far more extreme than anything we are experiencing today, and periods of cold that locked much of the planet in ice. It tells us that the ocean's chemistry has changed dramatically over geological time, with shifts in acidity, salinity, and dissolved oxygen that had profound effects on the organisms living in it. It tells us that mass extinctions, 5 of them in the past 500 million years, were driven in part by changes in ocean chemistry, and that the ocean, each time, eventually recovered, repopulating its depths with new forms of life adapted to the new conditions. The ocean's memory is written in stone and sediment and shell, and it stretches back farther than any other continuous record on Earth. The continents have been rearranged, the atmosphere has been transformed, entire lineages of life have appeared and disappeared, but the ocean has persisted through all of it, adapting and changing and continuing, the one constant feature of a planet that is otherwise in perpetual flux. Tonight, as you drift towards sleep, you are part of that continuity. The water in your body contains the same hydrogen atoms that were present in the ocean when the first life emerged over 3.5 billion years ago. Those atoms have been recycled through countless organisms, through clouds and rain and rivers and seas, through the bodies of fish and whales and plankton and tube worms and human beings, and they will continue to be recycled long after you are gone. You are, in a very real and physical sense, made of ocean. The boundary between your body and the sea is thinner than you think. The chemistry is the same, the water is the same, the atoms are the same. You came from the ocean. Every living thing on this planet came from the ocean. And when you sleep, when your consciousness dims and your body relaxes and your breathing slows to the rhythm of the waves, you are returning briefly and gently to something very old, something that knows you even if you do not know it, something that has been here since the beginning and that will be here at the end. The ocean is waiting. It has always been waiting, not with impatience, because the ocean has no impatience, not with expectation, because the ocean has no expectations. It waits the way water waits, passively, completely, without effort or intention, simply present, simply there, ready to receive whatever comes to it, ready to hold whatever is placed within it, ready to continue doing what it has done for 4 billion years, which is everything and nothing, all at once, in the dark. The surface of the ocean at night looks the same as it did when we began. The stars are still there, scattered across a sky so dark and so clear that you can see the faint glow of the Milky Way, our own galaxy seen from the inside, a river of light flowing across the heavens. The water is still there, moving with the slow, heavy rhythm that it has maintained for 4 billion years, a rhythm older than the continents, older than the atmosphere as we know it, older than every living thing that has ever drawn breath on this planet. The boat is still rocking, the air is still warm, and somewhere far below your feet, in the absolute darkness at the bottom of the world, everything we talked about tonight is still happening. The Challenger Deep is still there. The pressure is still 1086 bars. The temperature is still 1 to 4 degrees Celsius. The sea cucumbers are still drifting across the sediment, feeding on the slow rain of organic material that filters down from the productive waters above. The Xenophyophorus, those giant single-celled organisms, are still sitting on the seafloor, each one a biological marvel, a single cell the size of a human fist, doing whatever it is that xenophyophores do in the perpetual darkness of the Hadal Zone. Nobody knows exactly what that is. Nobody has watched one long enough to find out. The cameras visit for hours. The organisms have been there for millions of years. The timescales do not align. The hydrophones are still listening. Somewhere in the equatorial Pacific, the autonomous arrays that first detected the bloop in 1997 are still recording, still capturing every rumble and groan and whisper that the ocean produces. The upsweep is still rising and falling with the seasons, as it has done without interruption since at least 1991, a sound with no confirmed source, repeating itself year after year in the vast emptiness of the deep Pacific. Right now, at this moment, as you listen to my voice, that sound is being made. Something in the ocean is producing it, has been producing it for over 30 years, and will probably continue producing it long after the microphones that record it have corroded and failed and sunk to the bottom. The wreck of the USS Scorpion is still lying on the Atlantic seafloor, more than 3,000 meters down, 400 miles southwest of the Azores. The hull is still broken. The torpedo room hatches are still open. The nuclear reactor and the 2 nuclear-tipped torpedoes are still there, resting in the sediment, monitored periodically by remotely operated vehicles that descend to check for radioactive contamination. The 99 men who sailed the Scorpion on her last voyage are still there too, in whatever form the deep ocean has reduced them to over the past 57 years. The cold and the pressure and the darkness have preserved some things and dissolved others, and the full story of what happened on May 22nd, 1968 remains locked in that wreckage, inaccessible, perhaps forever. Some mysteries are not meant to be solved. Some questions are asked by the living and answered only by the dead. Somewhere in the deep waters of the North Pacific, a giant squid is hunting. It is possibly 10 or 12 meters long, with eyes the size of dinner plates and a beak that can slice through the flesh of any prey it can catch. It lives at a depth where no sunlight has ever reached, in water barely above freezing, at pressures that would kill a human being instantly. It has never been studied. No researcher has ever observed its hunting behavior in the wild. No one knows how old it is, how far it ranges, how it communicates, or how it reproduces. It is one of the largest invertebrates on Earth, and it is, for all practical purposes, invisible to science. It exists in the gap between what we know and what we suspect, a gap that, in the ocean, is wider than any canyon and deeper than any trench. Somewhere in the Arctic, a Greenland shark is swimming, slowly, deliberately, at a pace that would make a sea turtle look hurried. This particular shark might be 300 years old. It might be 400. It might have been born when Isaac Newton was writing the Principia, when the Baroque era was in full flower, when the idea that humanity would one day fly, let alone explore the deep ocean, would have seemed like the ravings of a madman. The shark does not know this. It does not know that centuries have passed since its birth, that empires have risen and fallen, that technologies have been invented that would be incomprehensible to the humans who were alive when it was young. It knows only the cold water and the slow current and the faint chemical traces of prey drifting through the darkness. It has been swimming this way for its entire life, and it will continue swimming this way until it dies, whenever that might be. The Greenland shark does not appear to age in the way that most animals do. Its body does not deteriorate in the familiar pattern of decline. It simply continues, year after year, decade after decade, century after century, moving through the ocean at 1 mile per hour, the slowest and longest-lived vertebrate on Earth. Somewhere off the coast of South Africa, the great white sharks that once patrolled False Bay are gone. The bay that was once one of the most famous shark-watching sites in the world is now largely empty of its signature predator. The orcas that drove them away may still be in the area, or they may have moved on to other hunting grounds, following the complex migratory patterns that orca populations maintain across the Southern Ocean. The seals that the sharks once hunted are more numerous now, their populations expanding in the absence of their primary predator. The fish that the seals eat are declining. The ecosystem is adjusting, shifting, rebalancing itself in the absence of an apex predator, as ecosystems always do, slowly and incompletely, and with consequences that ripple outward in ways that no one fully predicted. Somewhere in the Southern Ocean, near Antarctica, an iceberg is calving. The process might take hours or it might take seconds. A crack propagating through the ice at the speed of sound. A piece of frozen water the size of a building or a city block, or a small country separating from the continental ice sheet and falling into the sea. The splash, if it could be called a splash, generates a sound wave that travels through the SOFAR channel at 1,500 meters per second, crossing entire ocean basins, detectable by hydrophones thousands of miles away. The bloop was one such sound, amplified and transmitted by the ocean's own acoustic infrastructure, an icequake so loud that it was heard across the Pacific. Tonight, right now, similar sounds are being produced. Ice is cracking. Icebergs are breaking free. The ocean is carrying their acoustic signatures to instruments that are listening in the dark, adding each new sound to the vast continuous record of the ocean's voice. The hydrothermal vents along the mid-ocean ridges are still active. The superheated, mineral-laden water is still pouring from cracks in the Earth's crust, sustaining ecosystems that have no connection to the sun. The tube worms are still growing, their red plumes extracting dissolved chemicals from the vent fluid, their bodies harbouring billions of chemosynthetic bacteria that convert chemistry into life. Some of these vent communities have been active for decades, others are centuries old. Still others have gone dormant as the geological processes that fed them have shifted, leaving behind fields of empty tube worm casings and dead mussel shells, ghost towns on the ocean floor, monuments to ecosystems that thrived and then fell silent when the Earth's chemistry moved on. New vents are opening somewhere right now, new cracks in the ocean floor, new sources of heat and chemistry, new foundations for life in places where life has never existed before. And drifting through the deep water, carried by slow currents that take years to cross an ocean basin, the larvae of vent organisms are searching for these new openings, sensing the chemical signatures of hydrogen sulfide and dissolved minerals, following gradients of heat and chemistry toward homes they have never seen. Guided by instincts that are older than most species on the surface of the Earth, when a larva finds a new vent, it settles, it grows. A new community begins in the dark, at the bottom of the ocean, without any human being ever knowing it happened. The bioluminescence has not stopped. In the mesopelagic zone, between 200 and 1,000 meters, the deep scattering layer is alive with cold blue light, the flashes and pulses of billions of organisms communicating, hunting, defending, deceiving. During the day, this layer sinks deeper into the ocean, following the retreating light. At night, it rises toward the surface, following the plankton that rise to feed under cover of darkness. This daily vertical migration is the largest movement of biomass on Earth. Every single night, an immense column of life rises from the deep, feeds in the shallow waters, and descends again before dawn. It has been happening for hundreds of millions of years, and it will happen again tonight, and tomorrow night, and every night for as long as the ocean exists. You cannot see any of this from the surface. From the deck of a boat at night, the ocean looks like a flat, dark, featureless expanse. It looks empty. It looks still. It looks like nothing is happening. But beneath the surface, the ocean is more active at night than it is during the day. The migration is underway. The predators are hunting. The bioluminescence is firing. The vents are churning. The ice is cracking. The sounds are travelling. The larvae are drifting. The sharks are swimming, the squid are hunting. Everything is in motion, everything is alive, everything is connected, and none of it needs your attention or your understanding or your approval to continue. The ocean does not perform for us. It does not arrange its wonders for our convenience. It does not reveal its secrets on our schedule. It operates on its own time scale, at its own pace, according to its own rules, and if we happen to observe some fraction of its activity, that is our good fortune, not the ocean's intention. The deep sea was making bioluminescence for 540 million years before any human eye existed to see it. The hydrothermal vents were sustaining life for billions of years before anyone thought to look. The giant squid was hunting in the midnight zone while our ancestors were still figuring out how to make fire. The ocean does not need us, but we need the ocean. Not just for the fish we eat and the oxygen we breathe and the climate it regulates, but for the reminder it provides. The reminder that the world is larger than we are, that there are places on this planet right now, today, that no human being has ever visited, that there are creatures alive at this moment that have never been seen or named or described, that the boundary of human knowledge, which we sometimes imagine is pushing outward in all directions, closing in on a complete understanding of our world, is in fact an enormous irregular frontier with vast unexplored territories behind it, territories that are not on distant planets or in other galaxies but directly beneath our feet, separated from us by nothing more than water and pressure and darkness. The ocean is the last wilderness, not because it is untouched. We have polluted it, overfished it, warmed it, acidified it, and filled it with plastic and noise and chemicals. But it remains wild in the deepest sense of the word. It remains a place where human control ends and nature's dominion begins. It remains a place where we are visitors, and not always welcome ones. It remains a place where the unknown is not a theoretical abstraction, but a physical reality, a vast, dark, heavy, cold, pressurized reality that begins a few 100 meters below the surface and extends to the very bottom of the world. Tonight we visited that world together. We descended through the layers. We listened to the sounds. We traced the paths of lost ships and lost men. We met the creatures that live in the dark. We stood at the edge of the Challenger Deep and looked down into a space so deep that if you dropped a stone from the surface, it would take more than an hour to reach the bottom. We asked the question that every ocean explorer eventually asks: what else is down there? And the answer came back the same way it always does: we do not know. And that is the most beautiful answer the ocean has ever given. Now the descent changes. Not into the ocean this time, but into something gentler, into rest, into the kind of quiet that you came here looking for. The boat is still rocking. Feel that motion for a moment, the slow, steady, rhythmic sway of a vessel on calm water, port and starboard, back and forth. It is one of the oldest rhythms the human body knows. We evolved on a planet that is 2/3 water, in bodies that are themselves mostly water, and there is something deep in our neurology that responds to this motion, that recognizes it, that is calmed by it. Babies fall asleep when they are rocked. Adults fall asleep on trains and in cars and in hammocks that sway. The ocean rocks everything on its surface, slowly, patiently, without stopping. And it has been doing this since before the first creature crawled onto land, since before the first lung drew the first breath of air, since before there was anyone or anything to be rocked to sleep by it. The water beneath the boat is dark, not the darkness of a room with the lights off, where your eyes eventually adjust and shapes emerge from the gloom. The darkness of the deep ocean is absolute. It is the absence of all photons, the complete and total lack of electromagnetic radiation in the visible spectrum. If you could somehow transport yourself to the bottom of the Mariana Trench without a light source, you would see nothing. Not darkness as a colour, not even the faint neural static that your visual cortex produces when there is no input. Just nothing. An emptiness so complete that the concept of sight becomes meaningless. Your eyes would be open, and they would be receiving no information, and after a while, the distinction between open and closed would cease to matter. This is the darkness that covers most of the planet's surface. Right now, at this moment, the majority of Earth is dark. Not because of night, which passes, but because of depth, which does not. The sunlight that falls on the ocean's surface penetrates only the first few 100 meters, and below that the darkness is permanent. It was dark before the sun rose this morning, and it will be dark after the sun sets tomorrow, and it was dark 1,000,000 years ago, and it will be dark 1,000,000 years from now. The deep ocean's darkness is not a temporary condition. It is the default state of the largest habitat on Earth. Light is the exception. Darkness is the rule, and in that darkness the sounds continue. Close your eyes if they are not already closed, and imagine that you can hear the ocean. Not the surface sounds, not the crash of waves or the cry of seabirds, but the deep sounds, the sounds that travel through the water column at 1,500 meters per second, 5 times faster than sound travels through air. The low, resonant calls of baleen whales, singing songs that can cross entire oceans, songs whose purpose and meaning we are still trying to understand. Some whale songs are thought to be mating calls, others may be navigational, acoustic maps that the whales use to orient themselves in a featureless ocean. Others are simply unexplained, complex sequences of notes and rhythms that repeat and evolve over time, sung by animals whose brains are the largest of any creature that has ever lived. A blue whale's song can be detected from over 1,000 miles away. At this moment, somewhere in the ocean, a whale is singing, and the sound of its voice is travelling through the water in all directions, passing through the midnight zone and the abyssal zone and the Hadal zone, filling the darkness with a sound that has no audience except the ocean itself and whatever instruments we have placed in the water to listen. Below the whale songs there are other sounds, the slow, grinding creak of tectonic plates moving against each other measured in centimetres per year, but producing sounds that rumble through the Earth's crust and propagate into the water column. The hiss and roar of hydrothermal vents, superheated water erupting from the seafloor at temperatures that would melt lead. The sound muffled and distorted by the extreme pressure, but audible to the instruments that listen for it. The distant thunder of earthquakes, transmitted through the rock and the water, with a fidelity that allows seismologists to pinpoint the epicenter from thousands of miles away. The clicking of snapping shrimp, millions of tiny crustaceans that produce a collective noise so loud that it is one of the dominant background sounds of the shallow ocean, a constant crackle that sounds on a hydrophone like frying bacon, the low rhythmic pulses of ship propellers, the mechanical heartbeat of human commerce, audible even at the bottom of the Mariana Trench. The ocean is never silent. It has never been silent. Before humans existed, the ocean was full of sound. Before mammals existed, before fish existed, before anything with ears existed, the ocean was producing sounds, tectonic sounds and volcanic sounds, and the sounds of water moving over rock and sediment, and the chemical sounds of gases bubbling from vents. The ocean has been making music for 4 billion years, and it will continue making music long after the last human ear has gone deaf. Long after the last whale has sung its final song, long after the last hydrothermal vent has cooled and the last seamount has eroded to a flat, featureless plain, the sounds are there now. As you lie here, as your breathing slows and your muscles relax and the weight of the day begins to lift, the sounds are there, filling the ocean with vibrations that you cannot hear, but that are as real and as constant as the beating of your own heart. Let the rhythm of the boat carry you. Let the darkness of the deep ocean become the darkness behind your closed eyes. There is nothing to fear in this darkness. It is the same darkness that has cradled the oldest creatures on Earth, the same darkness where tube worms grow and giant squid hunt and Greenland sharks swim their slow, ancient path through the cold. It is the darkness of the Hadal zone, where life persists at pressures that should make it impossible, where organisms thrive without sunlight, without warmth, without anything that we would consider necessary for survival. Life in the deep ocean is proof that existence is more resilient, more creative and more determined than we ever imagined. If life can persist at the bottom of the Mariana Trench, in the cold and the dark and the crushing weight of 7 miles of water, then it can persist anywhere, including here, including now, including you. The ocean is older than anything you have ever worried about. It is older than your problems and your responsibilities and the things that kept you awake before you started listening to this. The ocean was here before language was invented, before cities were built, before agriculture was discovered, before the concept of money was created, before the first human being looked at the night sky and wondered what the lights were. The ocean was here, doing exactly what it is doing now, moving and sounding and holding its vast dark secrets in the deep, and it will be here long after every current worry has been resolved or forgotten or simply ceased to matter. There is something profoundly restful about that thought, about the knowledge that the world is larger than your problems, that the universe does not revolve around your anxieties, that somewhere, right now, at the bottom of the ocean, a creature that has never seen sunlight is going about its life with no knowledge of you, no awareness of the surface world, no concept of the stresses and pressures that keep human beings awake at night. The deep ocean does not know about your deadlines, or your bills, or your relationships, or your health, or the news. It does not care about the things that consume your waking hours. It simply exists, as it has existed for 4 billion years, vast and dark and patient and alive, and you can exist with it for a little while. You can let go of the surface. You can let go of the light and the noise and the constant exhausting stimulation of the waking world. You can sink, not with fear but with relief, into a quieter place, a darker place, a place where the only sounds are distant and rhythmic and old, where the only motion is the slow sway of the boat, where the only weight is the gentle invisible pressure of sleep pressing down on your eyelids and your shoulders and your chest, not crushing, not painful, but present, like the weight of a blanket, like the weight of the water column above the deep sea creatures that have made their home in the dark. The giant squid is not afraid of the dark. The tube worm is not afraid of the pressure. The Greenland shark is not afraid of the cold. These animals are perfectly adapted to their environment, and their environment is darkness and pressure and cold. They do not fight it. They do not resist it. They simply exist within it, calmly, naturally, the way you exist within the air and the gravity and the warmth of the world above the waves. The deep ocean is their home, and they are comfortable there, and they will remain there, doing what they do, long after tonight has ended and a new day has begun. You do not need to think about the ocean anymore. You do not need to remember the facts and the figures and the dates and the depths. They will be here if you want them. The Challenger Deep will still be 10,935 meters deep in the morning. The bloop will still have been an icequake. The USS Scorpion will still be resting on the Atlantic floor. The giant squid will still be hunting in the midnight zone. The Greenland shark will still be swimming at 1 mile per hour, as it has been doing for centuries. None of these things require your attention tonight. None of them need you to stay awake. The ocean is taking care of itself. It has been doing so for 4 billion years. It does not need your supervision or your worry or your wakefulness. It needs nothing from you at all, and that is perhaps the most comforting thing about it. In a world where everything seems to demand your attention, the ocean asks for nothing. It simply exists. And tonight that is enough. The boat rocks. The stars turn slowly overhead. The water moves beneath you, deep and dark and full of life, full of sound, full of secrets that have been kept for longer than any human mind can comprehend. Somewhere far below, in the Hadal zone, something is moving, something without a name, something that has never been seen and may never be seen. It does not know you are here, and you do not need to know it is there. You are both alive at the same moment, on the same planet, separated by nothing more than water and darkness and miles of depth. The darkness is not emptiness. It is fullness. It is a world teeming with life, with sound, with history, with mystery. It is the largest habitat on Earth, and it is directly beneath you, and it is as old as the planet itself. Let it hold you, the way it holds the creatures that live within it. Not with force, but with permanence. Not with light, but with depth. Not with answers, but with the comfort of knowing that some questions do not need to be answered tonight. The ocean will be here tomorrow. The mysteries will be here tomorrow. The deep will be here tomorrow. Tonight there is only the boat, and the stars, and the sound of the water, and the slow, heavy, ancient rhythm of the waves. Let it carry you. Let the surface fade. Let the light go. Sink. Not with fear, not with struggle. Sink the way the marine snow sinks through the water column, slowly, gently, drifting through the layers of the ocean, through the sunlight zone and the twilight zone and the midnight zone, through the abyssal darkness and the Hadal deep, all the way to the bottom, where everything is still and cold and quiet and old. The ocean floor is the quietest place on Earth, not silent, never silent, but quiet in a way that the surface world never achieves. The sounds that reach the bottom are filtered and softened by miles of water, the sharp edges of the world's noise rounded and smoothed until they become a distant gentle hum, a vibration so low and so faint that it is more felt than heard, like the pulse of the planet itself, like the slow, steady heartbeat of a world that has been alive for 4.5 billion years and shows no signs of stopping. You are part of this world. Your body is mostly water. The salt in your blood is the same salt that fills the ocean. The calcium in your bones was forged in the hearts of stars that exploded billions of years ago. The same stars whose light you see when you look up at the night sky. The oxygen you breathe was produced by organisms in the ocean, photosynthetic plankton that have been making oxygen for longer than there have been lungs to breathe it. You are connected to the ocean in ways that are chemical and physical and ancient, in ways that predate your species and your genus and your entire evolutionary lineage. Tonight, you are returning to that connection, not by diving, not by descending in a submersible or holding your breath or doing anything that requires effort or courage or technology. You are returning to it by letting go, by releasing the tension that the day has built in your body, by allowing your thoughts to slow and soften and blur, the way light blurs as it passes through water, the sharp edges dissolving into something gentler, something warmer, something that does not demand your focus or your analysis or your attention. The ocean does not judge, it does not evaluate, it does not compare, it simply receives. Everything that enters the ocean becomes part of it, mixed and dissolved and distributed through the vast interconnected body of water that covers the planet. The ocean does not reject anything. It absorbs everything. Tonight let it absorb whatever you brought with you. The stress, the worry, the noise, the overstimulation, the anxiety, all of it. Let the ocean take it the way it takes everything, quietly, completely, without comment or complaint. You are safe. The boat is steady. The water is calm. The night is deep and clear and full of stars, and the ocean is full of life, and the world is very old and very large, and your place in it, while small, is real and valid and enough. Sleep now. Sleep the way the deep ocean sleeps, which is not really sleeping at all, but simply existing in a state of profound, unhurried calm, a state where everything continues and nothing is forced, where the currents move and the creatures drift, and the sounds travel through the water without urgency or anxiety or fear. The ocean is here. It has always been here. It will always be here. And if this helped you find some peace tonight, I will be here next time you need it. Good night.